How is gravity just curved spacetime? Could bending spacetime make shortcuts? In the stillness of a cosmic night, one rule reigns quietly supreme. Nothing travels faster than light. This isn't a law written on any sign or etched in stone. It's woven into the fabric of reality itself. Imagine a beam of light, born from a distant star, racing through the vacuum of space. No matter how powerful a rocket or how advanced a starship we dream up, that beam of light will always lead the way. It's as if the universe has a pace, a calm but unbreakable speed limit set long ago, and all travelers must respect it. When we say nothing can go faster than light, we're speaking of something profound. Light moves at about 300,000 kilometers each second, a speed so great it's hard to truly fathom. At this pace, a photon, a particle of light, could circle the Earth 7 times in a single heartbeat. And yet, however fast this is, it's finite. It sets a gentle boundary on how quickly cause and effect can happen. If you send a message by flashing a light, or even by a simple movement, the universe ensures that signal won't outrun light's journey. It's as if the cosmos whispers, "Be patient," making sure every effect follows its cause in the grand cosmic order. This cosmic speed limit isn't about technology or effort. It's not like a horse that can be made to run faster with more urging. It's a fundamental property of space and time. Albert Einstein discovered that as things try to move faster and faster, strange effects begin to happen. Time itself will slow down for the traveler, and distances will stretch out, conspiring to keep that object from ever exceeding light speed. No amount of energy, no burst of fuel can break this rule, because approaching the speed of light changes the world around you in such a way that you never quite catch up to that ultimate pace. Think of it like this. The speed of light is not just the pace of a beam, it's the pace of information, of causality itself. If somehow you went faster, you could end up in a paradox, potentially seeing an event before it ever began, like hearing an echo before the original sound. So nature protects the sequence of events with this ultimate speed. Light speed is how fast the universe allows anything to influence anything else. In the silence of the void, it's a gentle but firm line that says, "This far, no further," to motion. Yet rather than feeling limiting, this rule gives the cosmos its structure and rhythm. It means distant stars twinkling in the sky are not just there in an instant. Their light has travelled, possibly for eons, to reach us, connecting us to the ancient past. When you gaze at a star, you're seeing it as it was hundreds or millions of years ago, because even light must take its time to journey across the vastness. In this way, the speed of light knits time and space together. It ensures the night sky itself is a kind of time machine, where looking far means looking back, all because of that quiet limit holding everything to a measured pace. So, in this quiet cosmic night, as we contemplate journeys to far-off worlds, we accept this rule as our starting point. The speed of light is the universe's way of keeping things in order, a natural speedometer built into the workings of physics. It's why, under normal circumstances, we cannot hop across the galaxy in an instant or chase a sunbeam and catch it. To dream of roaming the stars, we must first respect the simple truth that nothing, at least in the ordinary sense, moves faster than light. It's a gentle reminder of the vastness of space and the patience it demands. And yet, as our thoughts wander, we begin to wonder, if we cannot break this speed limit by brute force, might there be subtle, hidden roads that let us cheat it in another way? The universe's speed limit stands firm, But our curiosity now leads us to explore the very stage on which this drama plays out: space and time themselves. Let's take a step back now and consider the stage itself: space and time. The world we experience has 3 dimensions of space: length, width, height, and 1 dimension of time. Einstein showed us these aren't separate at all. They're interwoven threads of one tapestry called spacetime. Try to imagine it as a vast, smooth fabric stretching out in all directions. Every event, a star shining, a planet spinning, you listening right now, needs not just a place, but a time. Where and when are part of a single concept, fundamentally linked. Space and time form the gentle landscape through which everything moves. Now, this space-time fabric isn't a flat, rigid sheet. It can bend, stretch, and even ripple subtly. When nothing is around to disturb it, space-time is like a calm, flat plane. Objects and light travel in straight lines across it, minding their own business. But imagine placing a heavy ball on a soft trampoline. The fabric dips around it. Similarly, anything with mass or energy curves space-time around itself. A bowling ball on the trampoline causes a dent. If you roll a marble nearby, the marble will curve inward, drawn as if by an unseen hand. In reality, the marble is just following the curvature of the trampoline surface. In the same way, planets, light, and even apples, falling from trees, all follow curves in the space-time fabric, even though to us, they appear to move under the pull of an invisible force called gravity. If you roll a marble near that trampoline dent, it spirals inward. In reality, it's simply following the sloping surface. Planets orbiting a star are like marbles circling a dimple in a cosmic fabric. They are trying to go straight, but space-time's curvature guides their path into an orbit. Those paths that objects naturally follow in space-time are called geodesics. This is just a fancy word for the straightest possible path in a curved space. On Earth's surface, the straightest path between 2 far-apart cities might look curved on a flat map because Earth is round. Airplanes follow such geodesic paths, taking what looks like a curved route on paper, because they're traveling on the curved surface of our planet. In space-time, a geodesic is the path an object will take if nothing forces it off course, like a planet calmly orbiting the sun or a comet arcing through the solar system. These paths are the closest thing to straight lines space-time allows, even if they appear curved to our eyes. So when we say space-time has a shape or curvature, we mean the presence of mass and energy changes how those geodesic paths run. If space-time were perfectly flat and empty, 2 objects moving side by side would stay side by side forever. But if space-time is curved, their paths can bend toward each other or apart, like 2 marbles on a sloping surface gradually rolling together. This idea that where and when form a malleable fabric is one of the most beautiful insights of modern physics. It tells us space isn't just an empty stage with time ticking uniformly in the background. Instead, the stage itself can warp and evolve. Space can stretch like soft taffy, and time can flow at different rates depending on circumstances. These are gentle shifts for everyday conditions. You won't notice your kitchen clock ticking slower when you walk across the room. But across cosmic distances and extreme conditions, the bending of space-time becomes significant. Starlight passing near the sun bends ever so slightly, making distant stars appear in shifted positions during an eclipse. Time runs a tad faster in the quiet of interstellar space than it does on Earth's surface, where our planet's mass warps time just a little. Picture a massive star as a kind of valley in this space-time fabric. Light, traveling near it, dips into the valley and climbs back out, which we observe as a bent path. Thinking of space-time as a fabric or landscape is a mental picture to guide us. It's not a fabric you could touch, or a landscape you could walk on, but the analogy helps our imagination. It reminds us that distance and duration can change in subtle ways. The cosmos doesn't hand us a simple, rigid grid. It's more like a flexible quilt that responds to what lies on it. In our journey toward understanding wormholes and warp drives, this notion is crucial. If we're to find cosmic shortcuts, it will be by shaping and playing with this flexible fabric of where and when. Space-time, then, sets the scene. A gentle, ever-present medium through which we all move. It carries the imprint of every object in the universe, each one creating a small dent or slope that others can feel. Now that we have this picture of a unified, curving stage, we can delve deeper. We're ready to explore how gravity emerges from this picture, how the invisible grip we call gravity is nothing more than geometry in this space-time fabric. In this way, we'll see how nature uses curvature to guide the dance of planets, stars, and even light itself, leading us one step closer to the idea of bending that geometry for our own cosmic journeys. Gravity, the force that pins us to Earth and guides the planets around the sun, was once explained by an apple falling from a tree. In the story, a young Isaac Newton watches an apple drop and wonders if the same pull that brought it down also tugs on the moon. Newton imagined gravity as an invisible force reaching through space. For centuries, we pictured gravity that way, a mysterious hand drawing objects together across emptiness. But Einstein's great insight transformed this picture. He asked, what if there is no pull at all? What if the apple falls because Earth has curved the space-time beneath it, and the apple is simply following the easiest path downward? This idea was revolutionary, yet surprisingly simple. Instead of a force, gravity could be seen as geometry. Earth, with its mass, shapes space-time around it, like a heavy sphere resting on that cosmic fabric we imagined. The apple isn't being yanked by an invisible string. It's rolling down a gentle slope in space-time that Earth's mass created. If you were floating in a room with no windows, and that room was free-falling toward Earth, you wouldn't feel your weight at all. You and everything around you would drift, as if gravity had vanished. That's because you'd all be moving along the same curved path, falling together. Einstein realized that being weightless in freefall and floating in space far from any planet feel the same. In both cases, you're just following spacetime's curves without resistance. This equivalence, that freefall is just motion along the natural curves of spacetime, is at the heart of his theory. So mass tells spacetime how to curve, and curved spacetime tells objects how to move. A planet like Earth curves spacetime. The moon glides along a path on that curve, which to our eyes looks like orbiting. The sun, being far more massive, creates a deeper valley in spacetime, and the Earth circles within that valley. Even light, which has no mass at all, gets its path bent when it passes near a massive star or galaxy. In 1919, during a solar eclipse, astronomers observed starlight bending around the sun. The stars appeared slightly out of place. It was gentle confirmation that Einstein's geometric gravity was real. Space itself, warped by the sun, was nudging the starlight. Thinking of gravity this way fills the universe with a new kind of intuition. We're used to thinking of gravity as a pull, But here we replace that with curves and slopes in a landscape. Climb a mountain, and gravity weakens a bit. In our analogy, the slope of space-time is a little less steep up there. Venture out into space, and you eventually leave Earth's curve behind, floating freely. Come near a black hole, and you find an extreme, a deep pit in space-time from which not even light can climb out. All these scenarios are described not by stronger or weaker pulls in the traditional sense, but by how space-time is shaped in each place. With gravity understood as the shape of space-time, the way forward to thinking about cosmic shortcuts becomes clearer. If gravity can bend a path, or even trap light, could space-time perhaps be shaped in even more exotic ways? Einstein and others began to wonder, are there ways to make tunnels or bridges in this fabric, shortcuts that bypass normal distances? If gravity is geometry, maybe we could imagine geometries that connect distant points or move space itself. These questions once sounded like fantasy, but they naturally emerged from Einstein's new reality. The apple's simple fall hinted at a profound truth. Space and time, bent and curved, govern motion. And if one could control that curvature, who knows what paths might open? As we marvel at this insight, that gravity is not so much a pull as a push and slide along space-time's curves, we set the stage for bold speculation. Our minds drift to what might be possible if we could tweak those curves deliberately. It's time to gently step from the firm truths of Einstein's world into the imaginative realm of shortcuts and pathways through space. Armed with gravity as geometry in our toolkit, we are prepared to explore the earliest dreams of cutting across the cosmos through wormholes and warp drives, ideas that sprouted directly from this understanding of space-time. From the moment Einstein unveiled the curved nature of space-time, imaginative minds began to wander further. If gravity is geometry, could that geometry fold or connect in surprising ways? The dream of a shortcut through the cosmos, a path that sidesteps the long road between stars, was irresistible. These musings led to the concept of wormholes, often depicted in fiction as tunnels or doorways through space and time. The idea actually took root in serious physics early on. In 1935, Albert Einstein and Nathan Rosen discovered what looked like a bridge within the mathematics of general relativity, something connecting two separate points in space-time. It was as if the equations hinted at a tunnel through the fabric of the universe. This became known as an Einstein-Rosen bridge, and later, physicist John Wheeler coined the evocative term wormhole for such a tunnel. Picture a wormhole as a gentle passageway. You enter one mouth of the tunnel here and emerge from the other mouth somewhere else, perhaps light years away. In principle, it could even connect two different universes or two distant times. It's a captivating thought. Step into a quiet portal in your room and step out on a planet orbiting another star, all in a blink. For a while, wormholes remained a mathematical curiosity and a playground for storytellers. But as physicists examined them more closely, they found a catch. If a wormhole formed naturally in Einstein's universe, it would pinch off too quickly for anything, even light, to get through. It's like imagining a tunnel made of soft rubber that collapses before you can run to the other side. To hold a wormhole open wide and stable, the equations suggested something extraordinary would be needed. A kind of matter, or energy, unlike any found in normal experience. While wormholes tantalized with the idea of doorways through space, another notion for cosmic travel was brewing, one that didn't require a tunnel at all. Instead, what if you could surf on space-time itself? In fiction, this concept is often called a warp drive. Famously, ships in Star Trek zip between stars by warping space. In 1994, a physicist named Miguel Alcubierre asked a bold question. Could Einstein's equations allow a bubble of space to move faster than light, carrying a ship inside it? To the surprise of many, he found a theoretical solution. In Alcubierre's scheme, space in front of the ship would contract, bringing the destination closer, and space behind would expand, pushing the starting point farther away. The ship, nestled in a stable bubble between these distortions, would effectively ride a wave of curved space-time. Within the bubble, the ship isn't actually moving faster than light relative to its local space. It's space itself doing the heavy lifting, like a conveyor belt carrying the ship along. In Alcubierre's scheme, all the motion happens to space, not through space. The warp bubble idea was exhilarating. It suggested the cosmic speed limit could be bypassed not by breaking it, but by bending the rules of the road. If space can stretch and compress, maybe it can carry us along at speeds no conventional rocket could achieve. Yet, just like wormholes, the warp drive had a catch that became clear on closer inspection. The kind of curvature needed, especially that expanding space behind and contracting space ahead, didn't look easy to produce. In fact, calculations indicated it would require an exotic form of negative energy to create and sustain the bubble. In other words, both these dreams, wormhole tunnels and warp bubbles, demanded a kind of energy or matter that behaves in a way nothing we've encountered normally does. Still, the mere existence of these solutions in Einstein's theory lit a small flame of hope. They told us that our universe doesn't outright forbid shortcuts. It's just that the toll for using them is something truly out of the ordinary. Scientists and dreamers alike took heart in that. After all, every great journey begins with the thought that it might be possible. Wormholes and warp drives moved from pure fantasy to legitimate, if highly speculative, topics of research. They became the cosmic what-ifs that challenge our understanding of physics. What if we could actually find or create the peculiar stuff needed to build a wormhole bridge or power a warp bubble? Before venturing further down that road, we need to understand what exactly this exotic requirement is. Our next step is to gently unpack the idea of these strange energy conditions. A soft introduction to why our everyday matter won't suffice for holding open a tunnel in space or fueling a warp across the stars. What exactly is this exotic energy or matter that wormholes and warp drives seem to require? To approach it gently, let's first think about what normal matter and energy are like. In everyday experience, everything we see has positive mass or energy. Your body has mass, a star has mass, even a photon of light carries energy. Mass and energy, according to Einstein, are two sides of the same coin. Both contribute to gravity. Normal matter always produces an attractive gravity, pulling other matter toward it. Drop a rock and it falls to Earth because Earth's mass draws it in. This is how ordinary things behave. They have energy, they have mass, and their gravity pulls. Physicists formalize this idea with what they call energy conditions. These are basically guidelines in general relativity that say, under normal circumstances, you won't get weird things like negative energy in any small region of space. In simpler terms, an energy condition is like a rule stating you can't have less than nothing. If you take any tiny volume of space and tally up all the energy, including mass, since mass is energy too, inside it, the result should never come out negative for normal matter. It's a reasonable expectation. We don't see places with less than zero energy. Even empty space, the vacuum, has a baseline energy, but nothing that would drag the total below zero in a classical sense. Exotic matter is a catch-all term for stuff that would break these rules. It refers to matter or energy, with properties unlike anything we've seen in bulk. The hallmark requirement is having a negative energy density in some region. That phrase sounds abstract, but think of it like this. If normal mass is like a hill in space-time, causing objects to roll toward it, then negative mass or negative energy would be like a dip or an anti-hill, causing objects to be repelled. It would produce gravity that pushes rather than pulls. To hold a wormhole open, for instance, you'd want something lining the tunnel that pushes the walls apart against gravity's natural tendency to pull them shut. Ordinary matter can't do this. Pile in regular mass, and you only make the tunnel collapse faster under its own weight. You need something that behaves oppositely, at least gravitationally. One way to imagine it is to picture a tunnel through a mountain. It needs support beams to keep it from caving in. In a wormhole, space-time itself is the mountain that wants to close up. Exotic matter would act like those support beams, but ones that push outward rather than just hold up weight. They'd exert pressure to hold space open. Mathematically, that kind of outward push or tension shows up as negative energy in Einstein's equations. It's as if the support beams had to have less than zero energy to do the job. Negative energy sounds like something that shouldn't exist, and in daily life, we never see it. If you have $0, you can't have less than 0 physical dollars. However, physics allows some loopholes under special conditions. We'll get to those soon. The key point is that our theories don't absolutely forbid negative energy, they just make it very hard to come by. All the normal matter we know obeys the energy conditions. It has positive energy density. So to get a wormhole or a warp drive, we must step outside the realm of the ordinary. Scientists have names for various energy conditions, weak, null, etc. But what matters here is the essence. Wormholes and warp bubbles need stuff that violates those conditions. They demand an input into Einstein's equations that creates repulsive gravity effects. In plain terms, it's like sticking a negative number where normally only positives are allowed. The result is space-time bending in a novel way. Instead of curving inward to make a gravitational well, as normal mass does, it might curve outward or in some otherwise peculiar fashion. As exotic as this sounds, nature hasn't slammed the door completely. It might be possible, at least in theory, to have these strange conditions satisfied. But it is a tall order. No one has a jar of negative energy they can pull off a shelf. If exotic matter exists at all, it likely appears only fleetingly or under extreme conditions we don't routinely encounter. In essence, the requirement for wormholes and warp drives forces us to seek something that behaves almost magically by everyday standards. To proceed on our cosmic journey, we'll need to see if the universe offers any hints that such peculiar states of matter or energy can exist. And indeed, at the smallest scales, the quantum realm does offer some glimmers of hope. Subtle, tiny effects that suggest nature can, in special situations, dip a toe into the negative. Before we get carried away building cosmic tunnels, let's explore these delicate quantum phenomena that hint at the exotic. In the strange arena of quantum physics, what once seemed impossible becomes, in small ways, possible. On large scales, we never witness negative energy, but in the tiniest corners of reality, the rules loosen enough to allow slight exceptions. Consider the famous Casimir effect. If you take two uncharged, flat metal plates and place them extremely close together in a vacuum, just a few nanometers apart, something subtle happens. Normally, empty space is bubbling with quantum energy fluctuations. Particles and antiparticles flicker in and out of existence everywhere, even in a vacuum. But between those plates, only certain vibrations of these quantum fields fit. The plates quietly suppress some of the vacuum's usual humming. This leaves a bit less energy between the plates than in the space outside. In a sense, that gap has less than the normal amount of nothing. The energy there is lower than in free space, effectively a pocket of negative energy density. The result? The plates are gently pulled toward each other, as if the reduced energy between them creates a tiny low-pressure zone, drawing them in. This force is extremely small, but it has been measured in the lab. Nature, in this small and controlled way, allows an energy deficit, a hint of negative energy. Another quantum phenomenon involves what physicists call a squeezed vacuum or squeezed light. Normally, even empty space has a baseline level of jitter, random little fluctuations of energy thanks to the uncertainty principle. But using clever optical techniques, scientists can manipulate these fluctuations. In a squeezed state, they reduce the uncertainty, the jitter, in one aspect of a field, say the electric field of light, at the expense of increasing it in another. By squeezing the vacuum this way, it's possible to create moments and regions where the energy is actually lower than the usual vacuum level. It's as if, for an instant, the quantum vacuum in that spot becomes quieter than normal, dipping below zero on the energy ledger. Such negative energy states are fleeting and delicate, but they have been observed indirectly in experiments with lasers. For a brief moment, the usual constraints relax, and the vacuum gives up a little extra energy, leaving a tiny void of negativity before things return to normal. These glimpses of negative energy in the quantum realm are incredibly small and short-lived. The Casimir effect's force is minuscule. It takes very sensitive instruments to detect that gentle tug between plates. Squeezed vacuum states and other exotic quantum setups require finely tuned lab equipment and produce only whispers of an effect before the fluctuations rebound. We are far, far away from the science fiction idea of fueling a starship with bottled negative energy. Yet the significance of these findings is profound. They show that the universe does not categorically forbid negative energy. The door isn't locked, it's just very hard to open. Physics allows these strange conditions, but only in tiny amounts and for brief times. For scientists dreaming of wormholes and warp drives, these quantum effects are like a proof of concept on a miniature scale. They reassure us that exotic matter isn't pure imagination. Nature itself provides a small, tantalizing example. The challenge ahead would be finding a way to scale up something that quantum mechanics only lets us glimpse for now. Perhaps in the far future, technology or new physics could amplify such effects, sustaining negative energy in quantities large enough to be meaningful. For now, we have just a faint green light from the quantum world softly saying, this might be possible under the strictest conditions. With that encouragement, we return to our theoretical roadmap. How do we actually describe a wormhole or a warp bubble in the language of Einstein's theory? We do it through what's known as a metric, which is basically the code that tells space-time how distances and times are measured. If space-time is our cosmic highway, the metric is the chart that lays out the lanes, the curves, and the rules of the road. In short, the metric encodes the geometry of a given world. When physicists design a wormhole or warp drive on paper, they start by proposing a metric with the features they want, say, a tunnel connecting two regions or a moving bubble of space. The metric contains all the information about that hypothetical space-time, where a path might shorten travel, where time might speed up or slow down, and whether there are boundaries beyond which one cannot pass. Reading a metric is a bit like reading a very detailed map. There may be strange coordinates that only cover part of the territory, like how a flat map of Earth distorts or cuts off at the poles. In a wormhole metric, for example, you might find that a radial coordinate does something unusual, decreasing to a minimum and then increasing again, indicating a tunnel that has a middle point, a throat, and leads out somewhere else rather than ending. In a warp drive metric, you'd see in the math that space is contracting ahead of the ship and expanding behind it. One important thing a metric can reveal is whether there's a horizon or a singularity present. A horizon, like a black hole's event horizon, is essentially a hidden boundary in space-time, a one-way door beyond which events can't affect an outside observer. On a map, this is akin to an edge beyond which the chart doesn't extend. For a traversable wormhole, a well-crafted metric avoids such horizons along the travel path. You could, in principle, go through the tunnel and come out the other side without hitting a point of no return. In an idealized warp drive metric, there's no event horizon trapping the ship. Inside the bubble, physics looks normal, and in theory, the ship could stop or communicate with the outside at will, setting aside technical worries of creating or ending the bubble. The absence of a horizon in the metric would mean the shortcut is not hiding any gotcha that makes it unusable. By examining metrics, physicists can check if their imagined shortcut has any hidden problems. Does the wormhole pinch off anywhere, like a tunnel that narrows to nothing? Does the warp bubble involve a horizon or singularity that would spell trouble? The metric provides the answers. It's like stress testing our space-time design. If the math shows a singularity or horizon where we don't want one, that design might not be a truly traversable shortcut. In contrast, a well-behaved metric shows a smooth ride, at least mathematically speaking. We won't delve into actual equations here, but it's amazing that such abstract objects, pages of symbols defining a metric, correspond to whether a spaceship could, in theory, take a shortcut through the cosmos. By studying these metrics, we bridge the gap between imagination and the hard rules of physics. We've now gathered the core ingredients for our discussion: the universal speed limit, the flexible fabric of space-time, gravity as geometry, the dream of shortcuts, the need for exotic matter, the quantum hints of negative energy, and the theoretical maps, metrics, that describe these possibilities. With this foundation in place, we can set our sights on the road ahead. In the final part of this section, we'll take stock of where we stand and chart a gentle path from these principles toward the practical dream of traversing cosmic distances. In this gentle voyage, we've taken through fundamental ideas. We've built a base camp of understanding. We lingered on the speed of light, that quiet universal speed limit, and we imagined the very shape of space and time as something that can bend and curve. We saw gravity not as a mysterious pull, but as the sloping geometry of space-time itself. We allowed ourselves to dream of cosmic shortcuts, wormholes acting as tunnels and warp drives bending space around a ship. We acknowledged the steep price of such dreams, the need for exotic forms of matter or energy that push the limits of what we know. We even peered into the quantum world for tiny signs that this exotic stuff might not be pure fantasy. Piece by piece, principle by principle, we've assembled the toolkit needed to seriously discuss faster-than-light travel without leaving the solid ground of physics. Now, it's time to take these principles and see how they might form actual passageways. In the journey ahead, we'll move from theory toward envisioning practice. What would a traversable wormhole look like? And how might one keep it open? Could there be naturally occurring wormholes out there among the stars, waiting to be found? And what of warp drives? How far have scientists gotten in sketching out a real drive that could carry a ship to distant worlds? We'll delve into proposed designs, the details of the Alcubierre warp bubble and later refinements to it, the conceptual blueprints for wormhole stargates suggested by physicists like Kip Thorne. We'll weigh the energies required, by today's standards, truly astronomical amounts, and consider whether any loopholes or future breakthroughs might one day lower those barriers. This next phase of exploration will blend the speculative with the scientific. We'll stay grounded in what physics permits, yet let curiosity guide us through possibilities that read almost like science fiction. As we navigate these topics, our tone will remain gentle and unhurried. After all, we're charting routes through imagination as much as through space-time. By the end, we hope to travel from the fundamental principles we've learned through the hypothetical passageways those principles suggest, and finally to the threshold of practical considerations, however distant those remain. For now, we pause at this waypoint. Our minds have roamed from apples falling under gravity to the edges of black hole horizons, from the vacuum between tiny plates to visions of starships surfing space-time. It's a lot to take in, but it forms a coherent tapestry, a map of where we might go next. In the stillness of this moment, we can almost feel the hum of potential technologies and distant adventures stirring in the dark. Whenever you're ready, we will continue onward, following these cosmic highways from understanding into the realm of possibility. The path is set, and the stars await our next gentle steps. In our exploration of cosmic highways, we have seen how space might be gently bent or folded to shorten a journey. Now, another possibility comes into view, one even more mysterious and alluring. Instead of riding a wave of curved space around a ship, imagine a bridge that connects two distant shores of the universe directly. This is the idea of the wormhole, a tunnel through the fabric of space and time, offering a shortcut between faraway places that would otherwise be separated by light years. The concept feels like something out of a dream, a door opening in one corner of the cosmos and emerging in another. But it is grounded in real equations and serious speculation. A wormhole can be visualized as having two openings, often called mouths, and a connecting passage known as the throat. If you stood at one mouth, you might peer through and see a strange distortion showing whatever lies at the far end, as though looking through a shimmering portal. The two mouths could be in the same universe, or perhaps in entirely different universes altogether. Whatever the case, the wormhole's throat links them outside the usual flow of space between, providing, at least in theory, a breathtakingly efficient route from one place to another. It's a bit like finding a hidden hallway in a vast mansion that lets you step from one room to a far distant room instantly, bypassing the corridors in between. The idea of such a bridge in space-time first emerged from the mathematics of Einstein's general theory of relativity. Not long after black holes were recognized in Einstein's theory, physicists discovered that the math allowed a kind of tunnel as well. In the 1930s, Albert Einstein himself, together with Nathan Rosen, explored this concept. They found that the equations for a black hole hinted at a connection between two far-apart regions of space. On paper, the interior of a black hole could be linked to another place, or even another universe through a tunnel. This theoretical linkage was dubbed an Einstein-Rosen bridge, an early description of a wormhole. It seemed like science fiction, a cosmic bridge hidden in a black hole's equations. However, Einstein and Rosen's bridge was not the easy cosmic shortcut one might hope for. As originally formulated, this wormhole could only exist under extremely special conditions, and even then, only for the briefest moment. By the early 1960s, physicists John Wheeler and Robert Fuller showed that an Einstein-Rosen bridge is inherently unstable. Anything sent through would cause the tunnel to pinch shut almost as soon as it formed. In simple terms, This original wormhole wasn't traversable at all. It was a theoretical bridge that collapsed too quickly to be of any practical use. For decades, wormholes remained a tantalizing idea, seemingly forbidden as actual travel routes. They were cosmic bridges that nature allowed in theory, but snatched away in practice. Yet the allure never quite died. Scientists and dreamers kept wondering, could there be a way to build a more cooperative wormhole, one that stays open long enough for something, or someone, to get through? This question lingered without an answer for many years. In the 1980s, propelled in part by curiosity and even a nudge from science fiction, physicists revisited the wormhole concept with fresh eyes. A significant spark came from astronomer and novelist Carl Sagan, who imagined beings crossing the galaxy through a space tunnel and asked Kip Thorne whether such a thing could be plausible. Instead of dismissing the idea, Thorne took the challenge seriously. Together with his colleague Michael Morris, he set about designing a wormhole that a human or spacecraft could actually traverse. What emerged from that effort was a very different kind of wormhole, one engineered to be traversable. Unlike the Einstein-Rosen bridge tied to black holes, this hypothetical wormhole was not a one-time flicker doomed to collapse. Thorne and Morris formulated a theoretical structure that could, in principle, remain open and stable, a permanent tunnel through space-time. One key feature was the absence of an event horizon. There was no point of no return lurking inside. In a traversable wormhole, a traveller could venture in and eventually come back out, in either direction. This traversable wormhole design had other crucial characteristics aimed at making passage safe. It sidestepped any crushing singularity at the centre. There was no infinitely dense mass to tear the traveller apart. The geometry of the throat was designed to flare out at its narrowest point, creating a kind of gentle opening rather than a pinching trap. A person entering such a wormhole wouldn't be stretched or crushed. If built correctly, the tidal forces, differences in gravity across one's body, could be so small as to be hardly noticeable. Morris and Thorne calculated that these forces could be kept within comfortable limits, perhaps comparable to what we feel on Earth. In essence, they sketched out the requirements for a hospitable shortcut through space. When Thorne and Morris published their findings in 1988, presenting it partly as a teaching exercise, they ignited a surge of interest in wormholes as a serious topic in physics. What had been an obscure backwater of relativity theory began to blossom into an active field. Researchers realized that wormholes might not be mere mathematical oddities. They could be considered potential passages, governed by physical laws that one could probe through careful thought experiments. No natural wormhole has ever been found, but scientists have become increasingly skilled at exploring its implications. The traversable wormhole transitioned from pure fantasy toward the realm of theoretical possibility, still extraordinarily challenging and exotic, but not strictly forbidden by known physics. To be clear, even this traversable wormhole was, and remains, entirely hypothetical. It comes with enormous engineering and scientific challenges, some of which we will explore. Yet it gave scientists a framework to discuss wormhole travel in concrete terms. Questions naturally followed. How would a wormhole appear up close? What exotic substance might be needed to hold it open? What would a journey through one feel like? And would time itself flow differently for those who traverse this shortcut through space? This new concept opened the door to treating these once purely theoretical curiosities as something that perhaps, in the far future, could actually be constructed and used. It was a profound shift in perspective. A wormhole was no longer just a mathematical oddity, but a hypothetical passage one might dream of traversing. And so, wormholes moved from Einstein's musings to a central theme of our cosmic journey, promising a doorway through space, and possibly time itself. With this understanding in hand, we can delve deeper into the structure and subtleties of these cosmic corridors. Picture yourself approaching a wormhole and consider its architecture. In a sense, the wormhole's design is reminiscent of a tunnel carved through space. At each end, the space opens into a wide mouth. But as you move inward, the tunnel narrows down to a minimum size before expanding out toward the other side. This narrowest region is what physicists call the throat of the wormhole, the critical passage connecting the two realms. Think of it like an hourglass shape, wide at the mouths where you enter and exit, and constricted in the middle. The existence of a well-defined throat means the wormhole has a finite size at its most tight point, rather than pinching off completely. That finite opening is crucial. It's what allows the tunnel to remain passable instead of choking into a dead end. The geometry around the throat is a delicate balance. In a simple visualization, scientists often use an embedding diagram. Imagine taking a two-dimensional slice through the wormhole and representing it as a surface that you can draw. That diagram might look like two bowls or funnels whose bases are joined together. The bottom of each funnel touches at the throat, signifying the connection between the two distant spaces. If the wormhole were a straight cylindrical tunnel, the diagram would show a tube of constant radius. But a real wormhole's shape generally isn't that simple. Instead, space curves gradually inward as you approach the throat, reaching a minimum radius there, and then curves back outward. This flaring shape ensures that as you move through the throat, you emerge into the other side with space opening up again around you. This requirement that the tunnel flares out at the throat, rather than pinching tighter and tighter, is fundamental to a traversable wormhole. When physicists talk about the flare-out condition, they mean that the wormhole's cross-sectional area at the throat is the smallest it gets, and just beyond that point, the cross-section starts growing larger again. In intuitive terms, you can imagine walking through a narrow mountain pass that opens out into a broad valley on the other side. At the very center of the pass, you have the tightest squeeze, but then the path widens, allowing you to continue forward. Similarly, for a wormhole, the throat is that tightest squeeze, but crucially, it doesn't collapse shut. Instead, space opens out on the far side, letting travelers through. If this flaring out did not happen, the wormhole would effectively close off. A tunnel that keeps narrowing without flaring would mean a traveler going in gets stuck or crushed as the passage dwindles to nothing. In the language of geometry, the throat wouldn't be a true minimum. It would just taper into oblivion. Traversability demands that the throat have a definable radius, a minimum but non-zero size, and that just beyond that, the geometry expands again. One can think of the throat as a kind of spatial bottleneck that remains open. It's narrow, yes, but not impassably so. This concept distinguishes a viable wormhole from a non-traversable one. The latter might form a connection for an instant, but then pinch off, offering no way through. The traversable wormhole's throat is held open enough to be a permanent passage. The flare-out condition isn't just a curious shape, it has deep implications for the physics inside the wormhole. Normally, gravity caused by matter tends to do the opposite of flaring out. It pulls things together and can make space converge. For example, in a black hole, space funnels inward to a point, ending in a singularity. For a wormhole to flare outward at the throat, something must counteract that natural tendency to collapse. The walls of the tunnel, so to speak, need to push outward against the pull of gravity. This is why the wormhole's geometry hints at the need for unusual forms of matter or energy. In a very real sense, the throat is being propped open against the grain of gravity's usual behavior. It's as if the geometry at the wormhole's waist is saying, keep this path open. And to do that, it must violate the normal rules that matter and gravity follow. One way to think of it is to imagine traveling through the throat from one side to the other. As you pass the midpoint, you transition from moving inward into the narrowing to moving outward into the expanding space. There is a smooth changeover. You are never caught at a sharp edge or a true boundary. Space itself bends seamlessly from one universe or region into the other. If you were watching a beam of light travel through, you'd see it converge toward the throat and then diverge again after passing through the narrowest part. This bending of light and trajectories is a direct result of that flared geometry. It's almost as if space-time itself is acting as a lens at the throat, focusing and then defocusing beams that traverse it. To the traveller, the throat might appear as a region of increased curvature. The scenery around might distort oddly, but then things widen out and normalize as the far end comes into view. All of these geometrical features, the narrowing, the minimum radius, and the flaring out, come together to define a stable corridor through space-time. By describing the wormhole in terms of such shapes, physicists ensure the design has no hidden pinch points or dead ends. The mathematics insists that the throat's curvature and shape obey certain conditions, which are intimately tied to what kind of energy is present there. The fact that space flares outward at the throat is essentially a clue. It tells us that ordinary matter, which pulls space inward, won't suffice. To achieve this inverted, anti-gravitational shape of space, one must introduce something extraordinary. This insight naturally leads to the question, what sort of exotic substance or field could hold the throat open in this way? The answer lies in the realm of negative energy and unusual matter, a topic we will now explore. Having established that a wormhole's throat needs to be held open against gravity's instinct to pinch it shut, we come face to face with a profound question. What can possibly do the holding? The answer lies in what physicists politely term exotic matter. This is not exotic in the sense of rare spices or curious animals, but truly exotic in a physics sense. It behaves in ways no normal substance does. In particular, exotic matter would have negative energy density, meaning its gravitational effect is repulsive rather than attractive. Instead of pulling space together, it pushes space apart. If we could place a band or ring of such negative energy material around the throat of a wormhole, it would act like an internal scaffold, preventing the tunnel from collapsing. In essence, exotic matter provides the anti-gravity shove needed to counterbalance the usual pull of gravity. This idea of negative energy isn't mere fantasy. It actually appears in our physical theories, albeit in subtle ways. Under ordinary circumstances, we never encounter negative energy. Every object around us has mass and energy that produce positive gravity. But in the strange undercurrents of quantum physics, there are phenomena that allow for local regions of space to have less than the usual amount of energy, effectively below zero compared to normal empty space. One famous example is known as the Casimir effect. In this effect, two metal plates placed extremely close together in a vacuum experience a tiny but measurable attraction due to quantum fluctuations of fields in the space between them. The important part is that the energy density between the plates is actually lower than in normal empty space outside. We can say that the region between the plates has a negative energy density relative to the rest of the vacuum. Nature has, in a sense, created a small zone of less than nothing energy. This is a laboratory demonstrated phenomenon, not just speculation. The negative energy from the Casimir effect is incredibly small and fleeting, but it proves a principle. Our universe does permit, under special conditions, a sort of anti-gravitational energy. Physicists like Kip Thorne and his colleagues took encouragement from such ideas. They argued that if quantum physics allows even a whiff of negative energy in certain setups, perhaps an advanced technology could amplify that effect or accumulate enough of it to stabilize a wormhole. The calculations suggest you'd need an enormous amount of effective negative mass energy to hold open a macroscopic wormhole, far beyond anything the Casimir effect provides in a small device. But the seed is there. Exotic matter might be created or harnessed in forms we don't yet know, potentially through quantum fields engineered in extreme ways. For instance, hypothetical particles with negative mass, if they exist, or quantum field configurations spread over a wormhole throat could generate the necessary push. Crucially, exotic matter must violate what physicists call energy conditions. Basically, the typical rules that energy and mass normally follow. In everyday life and in standard astrophysics, these energy conditions always hold true. They're the reason gravity is always attractive. A traversable wormhole demands that we break those rules, at least in the vicinity of the throat. This sounds radical, and it is. However, because quantum theory entertains those brief episodes of negative energy, it's not off the charts impossible, it's just nothing we know how to do in bulk. To keep a throat pried open, one would need a belt of negative energy circling it. That belt would have to generate intense repulsive gravity outward, essentially acting like an inner lining that fights collapse. The stresses and pressures of such a substance would be unlike anything we can produce with known materials. One might wonder just how much exotic matter is required for a typical wormhole. Early rough estimates suggested it might take a mass energy equivalent to that of a planet or a star in negative form to stabilize a sizable wormhole, a truly astronomical requirement. Later, theoretical refinements sometimes found scenarios needing less, but any way you slice it, the amounts and densities are extreme. It's not the kind of stuff you can scrape up in a lab jar. We're talking about perhaps harnessing stellar-scale energy in forms that essentially counteract gravity. It could be that only a civilization with technology far beyond our own, or phenomena in the early universe, could muster such quantities of exotic matter. Even if one had the exotic matter needed, keeping the wormhole stable raises further concerns. Imagine you've constructed your wormhole with a ring of negative energy stuff holding the throat open. Now, what happens when something tries to pass through? As a spaceship, or even just a beam of light enters, it carries positive energy, normal mass and energy, into the tunnel. The structure must withstand that without buckling. The fear is that introducing any ordinary matter might start to neutralize some of the negative energy or perturb the balance. If too much normal matter accumulates in the wormhole, its gravity could start overcoming the influence of the exotic matter, narrowing the throat. Engineers of such a wormhole, if they exist, would have to ensure that their exotic stabilizers are robust enough to handle traffic. Perhaps they would design active systems that adjust the distribution of negative energy in real time, compensating for the mass of a ship as it passes, much like adjusting buoyancy when loading a boat. There is also the question of longevity and quantum stability. Wormholes might be prone to subtle effects that could erode their stability over time. The exotic matter could theoretically evaporate or get eaten away by quantum processes. Some analyses have suggested that wormholes could be metastable, lasting a long time but ultimately decaying, or that they might oscillate if disturbed, much like a stretched membrane that can wobble. If the wobble grows, it might lead to a pinch-off. In the worst case, a poorly stabilized wormhole might collapse as soon as too large a disturbance happens, perhaps snapping shut and destroying anything inside. Clearly, maintaining a wormhole would not be a passive affair. It might require continuous monitoring and control, a bit like maintaining the pressure in a deep-sea tunnel or the structural integrity of a space station. The exotic matter configuration might need to be tuned to keep the throat open against various stresses. All these considerations make one thing evident. Traversable wormholes demand a kind of substance and level of control that lies far beyond our current capabilities. To date, no experiment has produced large-scale negative energy, nor have we spotted any naturally occurring exotic matter in the cosmos. It remains a theoretical placeholder, something that our equations say is needed, but we don't know if the universe actually allows it in the necessary amounts. Some optimists point out that the accelerating expansion of the universe, driven by what we call dark energy, shows that the cosmos does have a form of repulsive gravity built in. Could an advanced civilization tap into that to create wormholes? It's speculative in the extreme. For now, the need for exotic matter is one of the biggest hurdles for wormhole travel. It's the requirement that makes many physicists suspect that usable wormholes might not be realizable. Still, the concept doesn't violate any known fundamental law outright. It sits on the edge of our understanding, tantalizing and uncertain. In sum, keeping a wormhole open appears to demand physics at the edge of what is possible. Negative energies and pressures that stretch our imagination. We've followed the logic from the wormhole's geometry to the inevitable conclusion that something special must anchor that geometry. If such exotic materials can't be found or created, traversable wormholes might remain forever in the realm of thought experiments. But if they can, a whole new domain of engineering would emerge, the art of stabilizing space-time tunnels. Assuming for a moment that this challenge can be met, we can turn our attention to the experience of journeying through a wormhole. After all, a tunnel, no matter how it's propped open, is meant to be travelled. What would that trip feel like for those on board? And what peculiar effects would they notice along the way? If a traversable wormhole can be kept open, the next question is what the journey through it would be like. One of the most important aspects is gravity's effect on a traveller, in particular, tidal forces. Tidal forces are the differences in gravitational pull between one part of an object and another. For a human, it could mean gravity tugging slightly harder on your feet than your head, for example. In a strong gravitational field, such as near a black hole, tidal forces become lethal. They stretch objects into thin strands, a grim process, whimsically known as spaghettification. But a well-designed wormhole would avoid this danger. By making the throat large and the curvature gentle, the creators of a wormhole could ensure that the tidal forces inside are tolerable or even negligible. In fact, Morris and Thorne showed that it's possible, in principle, to have a wormhole where the maximum tidal acceleration is no more than what we feel on Earth. In such a scenario, travelling through the wormhole would be no more physically stressful than riding an elevator or sitting in a car. This dramatic reduction in hazard underscores how gentling the curvature can turn a deadly gauntlet into a comfortable passage. Imagine now that you are an intrepid traveller about to step into a wormhole. As you approach the mouth, you might feel the slightest hint of gravity pulling you in, or perhaps pushing outward, depending on how the exotic matter is arranged. If the engineers did their job right, you wouldn't feel a sharp jolt or crushing force. Instead, you'd enter the mouth and find yourself in a smooth passageway. There might be a moment of disorientation as the familiar starfield behind you warps and disappears, replaced by an uncanny darkness, or perhaps a swirling vista of distorted light. The walls of the tunnel, if one can call them that, aren't solid barriers, but rather the gradients of space itself curving around you. You float or glide through, essentially in free fall, so your body feels weightless. Your stomach doesn't drop. Your heart might race, but more from excitement than from any physical strain. If the wormhole is short, the transit could be startlingly brief. You might barely have time to register the strange environment before a pinprick of light ahead blossoms into the exit. For example, a wormhole connecting 2 points dozens of light years apart might have an internal tunnel only a few thousand kilometers long. Even moving at a modest speed, say, a spacecraft coasting without heavy thrust, you could cross that in minutes or hours. Some wormhole scenarios even allow near instantaneous passage. A step through, and you're already at the other side. For a longer tunnel or a slower journey, you might spend some time inside. But without external reference points, it could be hard to tell how fast you're moving. In the smooth darkness of the throat, motion is relative. You could be drifting or zipping along, and it feels the same. Time inside the wormhole might feel oddly abstract. With no day or night, a minute could seem like an eternity, or vice versa. During transit, any tidal forces that do exist would be minor. Perhaps a gentle stretching along one direction and compression along the perpendicular, barely noticeable if you weren't looking for it. It's comparable to passing through the center of a planet. At midpoint, gravity from all sides cancels out, leaving you in a free-fall balance. Similarly, at a wormhole's midpoint, you could experience near-zero tidal stress, especially if the geometry is symmetric and engineered for comfort. As you emerge on the far side, gravity and environment might return to a more familiar pattern. If the destination mouth is located near a planet or star, you'd suddenly feel that body's gravity taking hold of you. More dramatically, if you exit in open space, you might continue drifting weightlessly until a new source of gravity influences you. Travelers would have to be prepared for such changes. For instance, stepping out of a wormhole that opens high above a planet might mean you're now in free fall towards the surface, unless you have a ship or thrusters ready. In most visions of wormhole travel, though, the mouths would likely be placed at safe points, perhaps in orbit around planets or at stationary positions, to avoid dumping passengers into dangerous situations. One fascinating aspect of wormhole travel is how it confounds the usual expectations of time for journeys. If you and a friend synchronize watches, and your friend takes a conventional spaceship to a distant star, while you take a wormhole, the difference will be extraordinary. Your friend might spend years or decades, even at near light speeds, to reach the destination, aging only slightly due to relativity, but arriving far in your future. You, using the wormhole, might step across and arrive essentially at the same time you left, maybe minutes or hours later from your perspective. You could, in theory, wave to your friend as they depart on their long journey, then pop through your wormhole and be there to greet them when they eventually arrive by conventional means, having waited perhaps centuries for them on that side. In a way, wormholes obliterate the travel time that normally separates events. They allow almost simultaneous connections across vast distances. It's important to note that while wormhole travel feels almost instantaneous to the traveler and, up to relativistic quirks, to external observers as well, it doesn't violate the laws of physics as we understand them, because the path you take isn't a straight line through normal space. You're shortcutting through a higher dimensional twist. Your personal clock might tick only a short while during the trip. When you compare it with a clock back home, you'll find you left and arrived nearly at the same time by that measure too. There's no time dilation to worry about, as there would be in a high-speed rocket trip. You haven't hurtled through space at near light velocity. You've simply stepped through a door in space-time. This also means there's no twin paradox scenario where one traveler comes home much younger than the other. That is, provided we refrain from manipulating the wormhole in ways that could twist time, a prospect we'll soon consider. In essence, wormhole travel shifts the concern from the passage of time to the conditions of the passage. We've traded the problem of crossing light years of space, which normally would require vast time and energy, for the problem of constructing a perfectly safe tunnel through space-time. If that tunnel can be achieved, then the journey itself becomes the easy part, potentially calm, quick, and almost routine. For the traveler, the experience could be almost serene. One moment you're at the mouth under familiar stars, and the next you step out under an alien sky of unfamiliar constellations. Your body feels fine, and your clock shows only a trivial amount of time has passed. Yet you've accomplished a journey that in any other way would have been utterly impractical. That profound contrast, the ordinary feel of the trip versus the extraordinary distance covered, might be the most remarkable aspect of all. Up to now, we've imagined a wormhole as a static gateway, but wormhole mouths are objects that can move through space. What if someone takes one end of a wormhole on a journey, say, puts it on a fast spaceship and flies around at near light speed, or leaves it near a massive planet for a while? The answer is both fascinating and troublesome. The two ends of the wormhole can end up out of sync in time. In essence, a wormhole can become a sort of time machine. To understand why, recall Einstein's relativity. Moving clocks run slow compared to stationary ones, and clocks in strong gravity tick slower than those in weaker gravity. So, if one mouth of the wormhole experiences a different gravitational pull or high-speed trip relative to the other, it will age differently. When it reunites with its twin, their clocks no longer agree on the time. Imagine this concrete scenario. You have two aligned wormhole mouths, A and B, initially synchronized. You keep mouth A at home on Earth, and you load mouth B onto a spaceship. The ship then accelerates and zips off on a high-speed loop through space, perhaps traveling out and back at a significant fraction of the speed of light, before returning to Earth. During that trip, due to time dilation, mouth B's internal clock, and any physical processes near it, run slower relative to mouth A. Maybe years have passed on Earth, but only a few months passed for the travelling mouth B. Now, when they are back in proximity, mouth B is effectively younger than mouth A. They are still connected by the wormhole tunnel, but one end is now a few years behind the other in time. This leads to a bewildering possibility. If someone now enters the younger mouth B and travels through the wormhole to exit from the older mouth A, they would emerge in the past relative to when they entered. In our example, suppose mouth B's clock is 5 years behind A's. A traveller stepping into mouth B, the younger end, and instantly popping out of mouth A could arrive 5 years earlier than they departed, as measured on Earth. Essentially, they have travelled back in time. Conversely, going the other way through the wormhole, from the older mouth A to the younger B, would propel a traveller into the future, relative to Earth time. The wormhole becomes a two-way time portal, at least until the mouth's time difference changes. This isn't just theory-mongering. It's a result that physicists like Kip Thorne deduced when exploring wormhole physics. A traversable wormhole, if it exists, doesn't come with a built-in arrow of time alignment. Each mouth is part of its local environment and will accumulate whatever time effects that environment imposes. In the thought experiment above, the wormhole essentially links two different slices of time. One end remembers less time than the other. The result violates no local laws of physics on the journey, Travelers through the wormhole still move forward in time from their own perspective, but globally, it creates a time loop possibility. The notion of wormhole time travel opens a Pandora's box of paradoxes. If you can step out of a wormhole before you stepped in, all the classic time travel conundrums rear their heads. Can you prevent your own departure, for example, or alter history? Such scenarios make physicists uneasy, to put it mildly. Some, like Stephen Hawking, have conjectured a chronology protection conjecture, which suggests that perhaps the laws of physics conspire to prevent such paradoxes. Maybe, if you try to turn a wormhole into a time machine, something catastrophic happens. For instance, vacuum fluctuations and radiation buildup might destroy the wormhole at the exact moment it could allow a trip to the past. In other words, nature might protect causality by vetoing operable time machines. Even without invoking mysterious cosmic censorship, one could see practical steps that any wormhole-using civilization might take to avoid time travel trouble. The simplest is, don't let one mouth run off on its own fast clock adventure. In practice, that could mean always keeping the wormhole mouths in similar gravitational potentials and relative rest. Essentially, you'd want to anchor the mouths, perhaps stationing them together or moving them in tandem so they share the same motion. If both ends experience the same history, they stay synchronized in time and won't develop those dangerous time offsets. That might involve putting each mouth in a protected, controlled location, like identical space stations far from massive bodies, and refraining from accelerating one without doing the same to the other. However, perfectly synchronizing two distant objects is easier said than done. Even sitting on Earth, two clocks will drift if one is on a mountain, experiencing slightly weaker gravity, and the other at sea level, stronger gravity. Over long periods, tiny differences add up. The same goes for wormhole mouths. Small relative motions or gravitational differences could gradually introduce time shifts. It might become routine maintenance to tweak and recalibrate wormhole connections. Perhaps there'd be devices monitoring the time offset between mouths and making minute adjustments, maybe by temporarily slowing the rate of time passage at one mouth via gravitational fields or other exotic means to keep them within safe sync. In essence, operating a network of wormholes might require a whole new discipline of space-time engineering and timekeeping. The drifting of wormhole mouths isn't only about time. There's also space to consider. If one mouth is not held in place, it could wander due to gravitational tugs or simple inertia. Picture setting up one wormhole mouth on Earth and another on a spaceship. If the spaceship isn't careful, it might carry its wormhole mouth far off course, making the exit location unpredictable or even stranding it light years away from any intended target. Even on a planet, a mouth might slowly shift due to orbits and rotations, if not corrected. Therefore, part of anchoring is literal, using thrusters, electromagnetic traps, or other mechanisms to keep each mouth exactly where you want it, relative to some reference frame. Keeping mouths stable, both in time and space, would likely be a top priority for wormhole custodians. One can envision elaborate facilities built around each mouth, containment rings holding them in alignment, shielding to protect them from stray gravitational influences, and calibration systems to compare their time flow. The moment any discrepancy starts to grow, alarms might trigger and usage might be paused until resynchronization is achieved. In a sense, a wormhole hub would be part observatory, constantly measuring space-time, and part traffic control, managing movement through the portal, which we will discuss more soon. Despite best efforts, the potential for time shifts can never be entirely dismissed unless wormholes themselves are impossible to begin with. It remains an open question whether physics truly permits a stable wormhole without inviting time travel loops. So far, no experiment or observation has hinted that such shortcuts exist in reality. It may be that every wormhole, if it tries to become a time machine, self-destructs or prohibits passage just at the critical moment. Or perhaps the universe does allow it, and we simply haven't encountered the cosmic fine print that prevents paradoxes. What is clear is that any advanced civilization dealing with wormholes would tread very carefully. They would treat the mouths as something needing careful stewardship, not only for structural stability, but for temporal stability as well. The last thing you'd want is your cosmic highway turning into a route to yesterday, with all the potential chaos that implies. In summary, wormholes present a double-edged sword. They promise nearly instantaneous travel through space, but they also threaten to tangle up time if misused. The safe operation of a wormhole likely means imposing strict rules, perhaps even laws of physics themselves enforce them, about not accelerating or gravitating one mouth differently than the other. This adds yet another layer of complexity to our cosmic engineering project. With that in mind, assuming we can keep our wormhole mouths stably in place and in sync, we can ponder how one might actually form and grow such a miraculous tunnel in the first place. How might a wormhole actually come into being? Since none have been observed directly, we are left to speculate with the laws of physics as our guide. One possibility is that wormholes could be relics of the universe's birth. The early universe was an almost unimaginably violent and exotic place. Quantum fluctuations and extreme densities might have momentarily warped space-time in all sorts of ways. Some theorists have suggested that tiny, primordial wormholes could have popped into existence during those first fractions of a second after the Big Bang. Most would have been fleeting and collapsed immediately, but a few might have survived. If so, they would probably be microscopic, threaded through the fabric of space like minuscule tunnels shorter than an atomic nucleus. Normally, such tiny wormholes would pinch off. But here's where cosmology offers an intriguing twist. Cosmic inflation. This was the epoch when the universe expanded exponentially fast. If a wormhole existed during inflation, the expansion of space could have stretched it enormously, like pulling taffy. A wormhole that was quantum-sized could, at least in theory, have blown up to macroscopic scale, perhaps even large enough to travel through. For a primordial wormhole to inflate and remain stable, however, something must hold its throat open during the stretching. One idea involves cosmic strings, not the string theory kind, but literal line-like defects in space-time that may have formed in the early universe, somewhat analogous to cracks forming as ice freezes. If a cosmic string with negative mass, an exotic hypothetical object, threaded through a tiny wormhole, it could provide the repulsive gravity to keep the tunnel from collapsing. Then, as inflation takes place, this wired wormhole might balloon out instead of pinching off. Think of a soap bubble being blown. If the soap film is strong enough, the bubble expands instead of bursting. In our case, the negative mass cosmic string, or some equivalent negative energy structure, would be that strengthening agent. It's a highly speculative scenario, but it gives a glimpse of how nature might create a wormhole without any engineers around. If natural wormholes exist around us, we might try to detect them indirectly, perhaps through the odd way they would bend light, or by unusual gravitational effects. So far, nothing conclusive has been seen. It could be that if primordial wormholes did form, most succumbed to instability or are just too small to notice. But let's entertain an even more audacious idea. An advanced civilization deliberately creating or enlarging a wormhole. How could that be done? The first challenge is to obtain a wormhole seed to start with. It might be easier to nurture a tiny wormhole than to spontaneously tear space and make a new one. Some proposals suggest that tiny wormholes might pop in and out of existence at the quantum scale all the time. a concept sometimes called quantum foam. Normally, they vanish almost instantly, but if one could be captured or stabilized for even a moment, perhaps by an intense burst of negative energy, it could be coaxed into lasting longer. Once you have a nascent wormhole, naturally occurring or manufactured, the next step is expansion. To grow a wormhole from microscopic to usable size, you'd need to feed it a tremendous amount of exotic energy. Think of prying open a small crack into a doorway. This might be done by creating a spherical shell of negative energy around the tiny throat and slowly pushing outward, stretching space without breaking it. The process would likely have to be very gradual and precisely controlled. Too little energy, and the wormhole stays too small to use. Too much too quickly, and you might destabilize it. The analogy of inflating a balloon is apt. Push in air gently and evenly, and the balloon expands. Push too hard, and it pops. In wormhole terms, popping would mean a catastrophic collapse, possibly yielding a burst of radiation or even a tiny black hole. So our hypothetical wormhole engineers would inflate their space tunnel with great care. During the enlargement process, the wormhole might need constant tending. Perhaps automated systems would monitor the throat's size and stability, adjusting the flow of exotic energy in real time. The shape of the wormhole would also have to be managed. You wouldn't want it twisting or pinching in odd ways as it grows. There might be magnetic fields or other fields applied to guide its symmetry, much as one might use molds or guide wires in a construction project. This part is deeply speculative. We're imagining technologies far beyond anything we know. But it's a reasonable extrapolation. Building a wormhole would be at least as complex as building a large particle accelerator or a space habitat, except here, the structure is space-time itself. Another question is, how do you decide where a wormhole goes? If you create one end in your laboratory, where does the other end appear? In fiction, wormholes are often depicted as portals linking predetermined locations. But in reality, if one somehow conjured a brand new wormhole, the other mouth might pop up randomly, or in a location dictated by the quirks of the creation process. One strategy to guide a wormhole might be to form both ends in the same place, and then physically move one to the desired destination. For example, imagine constructing a small wormhole in orbit around Earth, two mouths side by side. Then attach one mouth to a spacecraft and carry it to, say, Alpha Centauri, a journey that could still take decades or centuries with conventional propulsion. Once it arrives, you'd have a wormhole connecting Earth and the Alpha Centauri system. Essentially, you'd front-load the travel time by deploying the portal, after which transit becomes instantaneous. This leapfrog approach is sometimes discussed in theoretical circles. You pay the travel cost once to set up the wormhole, and then reap the benefits thereafter. The feasibility of any of this is highly questionable. The energy requirements might be astronomically large, perhaps approaching the energy output of stars, or the mass energy of planets converted to negative form. The precision needed would be mind-boggling as well. We're talking about manipulating space-time at a fundamental level, something that might only be achievable by civilizations with technology bordering on the miraculous, or leveraging physics we haven't yet discovered. Still, the concept gives us a framework. Either find a wormhole, perhaps a gift from the cosmos, and enlarge it, or create one through extreme quantum experiments and nurture it to maturity. Both paths are daunting. There are even exotic propositions in theoretical physics, hinting that wormholes and quantum entanglement might be related. The ER equals EPR conjecture by Maldacena and Susskind suggests that entangled particles might be connected by tiny wormholes. If that deep connection were true, it could mean that wormholes are woven into the fabric of reality in ways we don't yet understand. Perhaps future scientists will learn to manipulate entanglement to summon wormholes on demand. A wildly speculative idea, but it shows how exploring these concepts pushes at the edges of knowledge. For now, growing and guiding a wormhole remains a thought experiment. It's the ultimate infrastructural challenge, not just building a bridge over a river, but building a bridge through the universe. All this speculation underlines an interesting point. Wormholes might not be found, but made, or at least nurtured. If they are ever to be part of a cosmic highway network, intelligent intervention would likely be required. In science fiction, wormhole construction is sometimes depicted as routine for advanced species, perhaps by deploying devices that warp space on demand. Reality would be far harsher. We might find that even if physics allows wormholes, the practical hurdles are so immense that we remain confined to more conventional means, unless we ourselves evolve into the kind of beings who can wield planets' worth of energy and bend space-time with precision. Still, thinking through these challenges is more than just fantasy. It helps physicists test the limits of general relativity and quantum theory. Each thought experiment is a probe into what nature might permit. Having pondered how one might bring a wormhole into existence and steer it to a useful location, we should turn our attention to the very practical matter of using it safely. Creating a cosmic shortcut is one thing. Managing it day to day is another. In the next part of our journey, we'll consider what safeguards and procedures might be necessary to operate a wormhole corridor without courting disaster. Operating a wormhole safely would require forethought and safeguards. One immediate concern is radiation. A wormhole can act like a two-way funnel for all sorts of particles and rays. If one mouth is positioned in a high radiation environment, say near a star's corona or amidst energetic cosmic events, that radiation can pour through to the other side. Unchecked, a traveler stepping out of a wormhole could be bathed in a burst of intense radiation coming from wherever the opposite mouth resides. To mitigate this, wormhole termini might be established in relatively quiet locations, for example, well away from stars or high-energy sources, and surrounded by protective structures. One could imagine space stations around each mouth equipped with thick shielding, leaving only the immediate opening for vehicles to approach. These stations would filter or block dangerous emissions, perhaps magnetic fields to deflect charged particles or shutters that can close if a sudden flare is detected coming through the wormhole. Even more subtle is the issue of vacuum energy and what physicists call back reaction. The wormhole's very existence could alter the quantum fields around it, and energy might build up in unexpected ways. Stephen Hawking famously speculated about this in his chronology protection conjecture. He argued that if a wormhole were ever used in a way that allowed travel back in time, as we discussed might be possible by moving one mouth, quantum effects would go haywire. Virtual particles and radiation could loop through the wormhole and amplify exponentially, delivering a blast of energy that either destroys the wormhole or prevents it from being used as a time machine. In essence, the wormhole would self-annihilate or shut off right at the brink of allowing a time paradox. Whether or not nature enforces this strict rule, it highlights a general point. Wormholes might be prone to violent feedback if stressed by extreme conditions. Even in normal operation, sending a lot of mass or energy through a wormhole could cause stresses. Imagine multiple ships flying through at once, or a high-powered laser beam being shot through the tunnel. The influx of energy could momentarily perturb the wormhole's shape, perhaps narrowing the throat or inducing vibrations in the structure of space-time. If too much comes through too quickly, there's a chance the wormhole could become unstable. To avoid this, traffic might need to be regulated. Large vessels might only go one at a time, and perhaps they'd be required to pass through at controlled speeds. There could be something like a weight limit and a speed limit, not unlike a bridge. A wormhole authority, whether human or an AI guardian, might monitor the mass energy flow and keep it within safe bounds. Communication signals would also be coursing through the wormhole. Radio messages, data transmissions, effectively giving instantaneous communication between far-flung points. But even signals carry energy. If a wormhole network became a backbone for a galaxy-wide internet, for instance, one would have to ensure that the cumulative energy of trillions of data transmissions doesn't inadvertently heat or destabilize the throat. This might sound far-fetched, but it's the kind of caution engineers would need. It might be wise to establish communication protocols that limit high-power pulses, or to build in fail-safes that temporarily damp transmissions if sensors detect any sign of the wormhole oscillating. We can also consider deliberate misuse or accidents. What if something harmful is coming through the wormhole? For example, a burst of plasma from a solar flare, or, in a more malicious scenario, a weapon launched by some adversary through the portal. It would be critical to have a way to shut things down in a hurry. Perhaps each mouth would be equipped with a quick close mechanism. One could envision a giant gate or iris, like the shutter of a camera, that can seal off the mouth physically. Alternatively, the exotic matter sustaining the wormhole could be manipulated in such a way as to collapse the tunnel on command. That would be a drastic measure, essentially destroying the wormhole, at least temporarily. But it might be the ultimate emergency brake to prevent something catastrophic from transiting. However, collapsing a wormhole is not something you'd do lightly. It could release a tremendous amount of energy. Imagine the pent-up distortions of space-time snapping back. So, in practice, a gentler approach might be preferred. For instance, a field that can be activated to repel or slow incoming objects. A kind of force field at the mouth that gives operators a buffer time to react. In normal operations, there might be checkpoint stations at each mouth. Every ship or traveller might have to stop at the station, get clearance, and then proceed through, rather than just barreling in unannounced. This way, nothing unintended sneaks through, and any potential hazard can be assessed. An important safety aspect is monitoring the wormhole's health. A network of sensors would likely be in place to measure things like the throat diameter, the distribution of stress within the wormhole, and any signs of exotic matter depletion. If the wormhole's geometry started to oscillate or deform beyond set limits, these sensors would trigger alarms or even automatic shutdown procedures. Perhaps the station AI would announce a temporary closure for maintenance, pausing travel until stability is restored. Maintenance might involve pumping additional exotic matter into the throat or retuning whatever field configurations keep it open. One can envision an entire protocol for wormhole emergencies. For example, if radiation beyond a certain threshold is detected coming from the other side, the mouth might seal and vent the radiation into space. Imagine a kind of airlock system for radiation. If a vehicle gets stuck or disabled in the throat, though the concept of stuck in space-time is tricky, it could be that a ship loses power mid-transit. Perhaps small robotic drones or built-in gravity gradients could nudge it along to prevent an obstruction. Just as tunnels on roads have procedures for breakdowns or accidents, a wormhole might need contingency plans for anything that could go wrong within. There's also the matter of coordinating travel through potentially multiple wormholes. If a future civilization operates many wormhole routes, you wouldn't want two wormholes opening into each other by accident, or one mouth being confused for another. So navigation and labeling become safety issues. Each wormhole pair might have unique identifiers, and traffic control would ensure that, say, only the intended destination's mouth is open to receive a traveller. Possibly, wormholes could even be temporarily turned off, not literally closed, but put in a state where traversal is locked, when not in use, or when maintenance is ongoing. This could prevent unintended crossings or reduce the baseline stress on the system. In summary, managing a wormhole is akin to operating a combination of a power plant, an airport, and a high-security facility, plus some unique twists of its own. Radiation shields, feedback dampers, mass flow regulators, emergency gates, and rigorous monitoring would all be part of the design. One might imagine a control room where operators, or advanced AI systems, watch over readouts of space-time metrics and energy levels, ready to intervene at the slightest anomaly. The wormhole is a gateway of unparalleled convenience, but with that comes the responsibility to ensure it remains benign. The last thing anyone wants is an uncontrolled wormhole accident, whether that's a burst of lethal radiation, a collapse that strands people light years from home, or a causality-violating loop. Fortunately, by anticipating these dangers, such a facility can be governed with layers of safety measures. In doing so, it transforms from a wild cosmic phenomenon into a reliable piece of infrastructure, a cosmic bridge that people can use with confidence. Having secured our hypothetical wormhole with safety nets and procedures, we can finally picture it as a stable corridor. Now the focus shifts to actually traveling and finding one's way through that corridor. In the final stretch, we will imagine what navigation is like inside a wormhole, how travelers ensure they reach their intended destination smoothly. Navigating through a wormhole presents challenges quite unlike those of ordinary space travel. Inside the wormhole, familiar reference points vanish. You can't rely on distant stars to orient yourself, because their light doesn't penetrate the tunnel in the usual way. In fact, as you approach a wormhole mouth from the outside, you might see a shimmering lens-like effect. The opening could show a warped view of the region around the other end. Astronauts have described it in hypothetical scenarios as looking into a crystal ball where another sky is visible. This is actually a boon for identification. The eye of the wormhole might glow with the light of its destination. For example, a wormhole linking to a galaxy with a distinctive nebula might show that nebula's hues faintly in its core. But once you're inside, those external vistas fade or contort. The space within is curved back on itself. Looking ahead, you primarily see the glow of the exit, and looking back, the entrance you came from. Turn your head sideways, and you might catch distorted glimpses of the same exit or entrance repeated strangely, as light rays wind their way through the curved space. In such an environment, inertial guidance becomes a traveler's best friend. Spacecraft, or even individual explorers, would depend on onboard instruments, gyroscopes, accelerometers, and computerized guidance to maintain orientation and trajectory. If you're piloting a ship, you likely have a pre-programmed course, essentially a straight line from entry to exit, since the ideal path through a symmetric wormhole is straightforward. Deviating significantly isn't advisable. You wouldn't want to graze the edges of the throat. Not that there are physical walls in the normal sense, but the curvature increases toward the periphery. Thankfully, in a well-constructed wormhole, gravity should guide anything that enters toward the other side. Still, minor course corrections might be needed if the wormhole has any twists. Imagine the tunnel bending slightly. You'd want to adjust so that you don't end up approaching the exit at a weird angle or orientation. Here, a beacon at the far end could help. Likely, there would be a navigation beacon broadcasting from the destination mouth, sending a signal down the throat to tell incoming travelers, "This way out." Your ship's instruments could home in on that signal to ensure you stay aligned with the exit. For a person inside without a ship, say some hypothetical scenario where an individual is traversing on foot or in a suit, the experience would be akin to moving through a featureless tunnel. You might even tether yourself to a guideline, perhaps a cable that was laid through during construction to avoid drifting aimlessly. In the darkness or dim glow, there would be few cues to tell you how far along you are. Only your equipment's readings and the growing light of the exit give you feedback. It would be easy to become disoriented if you spun around. With no fixed stars, one could lose the sense of up or down. But since gravity inside might be negligible or very symmetric, you wouldn't feel an up or down strongly anyway. Mission protocols would probably emphasize, keep moving in the direction of the exit beacon, don't make sudden lateral moves, and trust your compass, or whatever passes for a compass when magnetism is irrelevant and only inertial guidance counts. Navigational maps for wormhole travel would look very different from normal star charts. Instead of routes snaking through three-dimensional space between stars, you'd have marked gateways and instantaneous links. A pilot planning a journey would consult a chart of wormhole connections, a network diagram more than a traditional map. For instance, it might show that Earth's wormhole station connects to a hub in another galaxy, from which several other wormholes fan out. Each wormhole's endpoints would have unique identifiers or names, much like airports do. Each wormhole's endpoints might be given designations like Sol 1 for the Earth-side mouth and Centauri 1 for the other end at Alpha Centauri, for example. Before entering, travelers would receive data on the destination's conditions, local time, orientation differences, and any known hazards. Orientation differences are an interesting point. You could enter a wormhole upright relative to Earth and emerge sideways relative to the distant planet if the mouth there is oriented differently. Ships might have to be ready to adjust their attitude immediately on exit. Because wormhole travel bypasses normal space, traditional navigation by stars is replaced by navigation by network. Think of driving through a tunnel. You don't navigate by landmarks inside the tunnel. You simply follow the tunnel until it ends, then resume normal navigation. Similarly, a spaceship entering a wormhole simply commits to the exit path, and then, once on the other side, refers back to normal star charts. That said, near the mouths, visual cues and signposts could be very useful. Approaching a busy wormhole terminus might resemble approaching a space station or a port. There could be a visible structure around the mouth with lights, indicators, and even a holographic label announcing the destination or wormhole name. As fanciful as that sounds, it's practical. It prevents confusion if multiple wormholes exist in proximity. You wouldn't want to head into the wrong cosmic tunnel. We can also imagine communication beacons set just outside each mouth to guide travelers in. A spaceship might hail the wormhole station, a bit like contacting air traffic control, requesting permission to transit wormhole. The station would respond with the current status, perhaps confirming that the far end is clear and that no one is coming the opposite direction. Once inside, direct communication with the outside might drop off. The walls of space-time might not carry radio signals the same way. But the exit beacon ensures you know where you're headed. Some designs propose threading communication lines or repeaters through the wormhole, allowing a constant link from end to end. This could help coordinate multi-ship convoys. The lead ship could send back updates, halfway through all clear, that get relayed to those behind. Despite the strangeness, navigation through a well-maintained wormhole should, ideally, become routine. It might even be simpler in some respects than ordinary space travel. There are no obstacles inside, no meteorites or debris, no need for continuous propulsion if you're in freefall. The key is just entering and exiting correctly. Pilots would still train extensively for it, learning how to interpret instrument readings in the absence of normal cues, and practicing in simulators that mimic the optical distortions of wormhole travel. There could be stories of early adventurers who got disoriented or nervous in the featureless tunnel, only to emerge safely moments later, feeling a bit foolish. Over time, procedures would evolve until traversing a wormhole is about as dramatic as riding an elevator. You feel a slight motion, the lights blur for a bit, and then the doors open to a new world. One can imagine the first few journeys being monumental, full of awe and careful step-by-step navigation. But eventually, those journeys might blur into the background of everyday experience. Future travelers might barely give a thought to the physics. They'll simply follow the guidelines, watch the signals, and trust that they will step out the other side as planned. Still, even in that future, some travelers might press their faces to the viewport or display as they go through, marveling at the strange sight of a universe in between, however empty it appears. The wormhole might be routine, but it will never be trivial, for it literally bends reality to human or alien will. Navigating it safely is the final piece of the puzzle that allows these cosmic highways to truly function. As our journey through the concept of wormholes comes to a close, we can step back and appreciate the full panorama. From the theoretical underpinnings and physical requirements to the practical challenges of travel and management. Wormholes, together with ideas like warp drives, represent humanity's dream of transcending cosmic distances. They force us to grapple with deep truths about space, time, and energy. While they remain speculative, each thought experiment brings new insights. And who knows, perhaps one day, what we've imagined here will guide real explorers, charting safe passage through the cosmic web. Until then, we remain travelers in our minds, navigating these wormholes in theory, and holding on to the hope that one day the universe may open its doors for us in reality. The discussion drifts from tunnel-like wormholes to a different, and in some ways, even stranger idea. Instead of opening a hole through space, why not bend space itself into a moving wave? Imagine placing a ship inside a region of space that surfs a distortion, space contracting in front of it and expanding behind. This is the essence of the warp drive notion. In theory, such a drive would stretch the fabric of space-time in a wave, compressing the space ahead of a craft while expanding the space behind. The ship, nestled in a stable pocket of ordinary space, a warp bubble, would ride this wave across the cosmos. It's as if the ship remains still locally, but the space around it carries it forward. By cleverly manipulating space-time, the vessel could effectively rush toward its destination without ever technically breaking the speed of light in its immediate vicinity. The concept sounds like science fiction, yet it emerges straight from the equations of general relativity, first proposed in 1994 by physicist Miguel Alcubierre. He showed that Einstein's laws of gravity allowed this peculiar solution, a warp bubble that could, at least on paper, zip faster than any light beam across the same distance, all without violating fundamental physical laws. The idea of warping to a distant star was no longer just fantasy. It had a foothold, however speculative, in real physics. To picture it, think of space as a vast, stretchy fabric. An Alcubierre warp drive would pinch that fabric in front of the ship and pull it taut behind. The result is like riding a moving platform. The ship itself isn't blasting forward through space. Space is carrying the ship along. Inside the warp bubble, the spacecraft sits in its own little realm of flat, undisturbed space. All the wild action, the stretching and squeezing, happens at the bubble's edge, not within. In principle, this means anyone aboard wouldn't sense the violent rush. There'd be no acceleration jolt, no crushing G-forces. The bubble's interior is an inertial frame, just like floating in deep space. The crew could sip coffee and stroll the cabin as if the ship were parked, while outside the bubble's space-time itself hurtles them onward. This trick neatly evades the normal limits of motion. According to relativity, Nothing can locally move faster than light. But here, it's space doing the moving. Space itself can expand or contract without that restriction, as it did in the rapid inflation of the early universe. So a warp drive doesn't propel the ship through space faster than light. It drags a chunk of space along, making it appear as though the ship outraces light from an outside perspective. A light beam travelling outside the bubble still zips along at light speed, but the bubble and ship can arrive ahead of that beam because the distances have been warped smaller along the way. It's a bit like a clever cheat, arriving sooner not by running harder, but by shortening the road. This elegant picture, expanding space behind, contracting ahead, is often explained by analogy. Some liken it to surfing. The ship rides a space-time wave, similar to how a surfer rides an ocean swell. Others compare it to moving walkways in an airport. You walk at normal speed on the conveyor, the ship's local space. But the conveyor belt, the ship's local space, warped space-time, carries you forward faster than your footsteps alone could. However it's visualized, the warp drive idea tantalizingly suggests we could beat the cosmic speed limit by changing the venue of travel. If one could generate the right kind of space-time wave around a craft, whole star systems might be within reach in a traveler's lifetime. The term warp drive itself, long a staple of science fiction, suddenly gained scientific weight. Alcubierre acknowledged he was inspired by the fictional warp drives of Star Trek when he formulated his equations. Yet unlike pure fantasy, his solution obeyed Einstein's equations, with a few enormous catches that we'll soon address. For the first time, faster-than-light travel, as opposed to instantaneous teleportation or wormhole shortcuts, had a mathematical blueprint. The universe wasn't explicitly forbidding it. It was offering a profoundly difficult, but seemingly not impossible loophole. Still, one might ask, why would compressing and expanding space actually move the ship? In Alcubierre's model, the contraction ahead of the bubble creates a kind of downhill slope, while the expansion behind produces an uphill push. The bubble is effectively squeezed from behind and pulled from ahead, nudging it along. There's no engine pushing the ship in the traditional sense. The drive warps space itself to impart motion. From inside, it would feel like drifting freely, even as the outside world races past. In a way, it's like sitting in a calm eye of a storm. The winds of space-time blow around the edges, but the center, where the ship rests, is tranquil. Because of this, the usual effects of near-light speed travel, like time dilation, are expected to be minimal for those inside the bubble. The ship isn't really speeding through local space, so the crew's clocks tick normally, and they wouldn't notice anything odd about time. They could traverse light years in what feels like weeks or months of onboard time, without suffering the relativistic slowing of time that affects a ship moving conventionally at high speed. Of course, from the outside viewpoint, the ship's trip is superluminal. It gets there faster than any light signal could, but the crew's experience inside remains comfortably slow and steady. This is a crucial distinction. Warp travel cheats the light speed limit in global terms, getting somewhere faster than a light beam would in normal space. Yet it never asks any object to locally break that 299,792 kilometers per second rule. In theory, it's all perfectly consistent with relativity, which is part of why the idea caused such a stir. By the late 20th century, after decades of being told FTL travel is impossible, scientists suddenly had a model that said, maybe not impossible, just really, really hard. The Alcubierre warp metric was a solution to Einstein's field equations, an exact recipe for space-time curvature that produces this bubble. The excitement was palpable. Could humanity actually build this? What would it be like to ride a warp bubble to other stars? Before we dream too far ahead, we have to grapple with those catches mentioned earlier. The equations allowed the warp bubble, but making it a physical reality introduced daunting problems. To start with, this space-time bending ride isn't something you can just turn on with conventional energy or technology. It demands exotic ingredients and gargantuan energies. In Alcubierre's analysis, to create the expanding and contracting regions of space-time, one needs a type of energy density that's, well, outside the boundaries of what we know how to produce. Specifically, it calls for negative energy, an exotic form of matter or field with less than zero energy density. This isn't something you can pour into a fuel tank. Negative energy isn't science fiction magic. It does appear in physics, for instance, in the Casimir effect between closely spaced plates, but only in tiny amounts and fleeting circumstances. The warp drive requires vast quantities of it, arranged just so, to warp space on a macroscopic scale. That's our first hint that actually constructing a warp drive could be far beyond our reach. And even if one procured this bizarre fuel, there are deeper practical obstacles. Early analyses uncovered a fundamental issue. There's no known way to start a warp bubble, at least not from within our normal, unwarped space-time. Alcubierre's math describes a bubble already in motion. But how do you create it around a ship in the first place and set it off? As one scientist quipped, it takes a warp drive to make a warp drive. In other words, you might need to prearrange the exotic matter in just the right configuration before the bubble can exist. One cannot simply flip a switch and conjure a space-time wave where none existed. The equations suggest you'd have to have the warped region somehow assembled in advance. This chicken and egg problem means the first trip to any destination might not be possible by warp drive. You might have to travel there the slow way, or send devices ahead, to set up the conditions that allow a warp bubble to form for subsequent journeys. It's like laying down tracks for a railroad. The rails must be in place before the train can go. In the case of warp travel, laying down the tracks could mean distributing exotic energy along the route or having apparatus stationed ahead of time. Such requirements start to dampen the carefree vision of warp ships flitting anywhere at will. They might be confined to pre-prepared corridors, at least until a vast infrastructure is established. We also confront the unsettling realization that, once a warp bubble is cruising along, those inside might be effectively sealed off from the outside universe in strange ways. At superluminal speeds, a warp bubble creates a kind of horizon, analogous to the event horizon of a black hole, forming a one-way boundary around itself. Signals from inside the bubble can't get out ahead of it, because even light can't outrun the bubble's leading edge. This means the ship's crew couldn't send a light-speed message or a laser beam forward outside the bubble to influence anything or to communicate. If you suddenly realized you were headed toward a dangerous obstacle, you couldn't steer away by conventional means or radio a warning ahead. You'd be along for the ride until the bubble naturally dissipated. In essence, an Alcubierre bubble in superluminal mode makes its occupants causally disconnected from the space in front of them. That raises obvious control issues. How do you navigate a ship that can't poke its head out to see or signal where it's going? Jose Notario, a physicist who studied warp metrics, pointed out that inside such a bubble, you couldn't even control or halt your journey by any influence from within. The front of the bubble is off limits to your commands. It's a bit like being on a runaway train with no communication to the engine. Unless the bubble was programmed from the start to drop you out at a certain point, you'd have no way to stop early or change course mid-journey. This casts the warp ride in a more eerie light. The bubble would be a silent, self-contained pocket, its occupants unable to interact with the universe outside until the ride is over. What would it actually feel like, though? inside that bubble. If all goes well, surprisingly little. As mentioned, there'd be no acceleration felt when the warp field activates. The crew might only know they'd begun the journey because external light would do odd things. Some calculations suggest that at true superluminal speeds, the view outside might fade or go strange. Light from stars ahead can't reach into the bubble normally. The bubble is outrunning their photons. The front edge of the warp might act like a horizon that nothing can penetrate, meaning the crew looking out the forward windows could see only darkness, an endlessly black void, until the bubble slows down. Perhaps only a dull glow or a shifted halo of radiation would outline the bubble's boundary. Behind the ship, any light trying to catch up would likewise struggle, possibly reddening into obscurity. In essence, at faster-than-light rates, the bubble could be walled off by blackness on all sides, a black bubble carrying a shining starship inside. This speculation aligns with the idea that a warp bubble might trap light similarly to a black hole's event horizon, except the roles are reversed. The ship is inside the horizon moving with it. It's an unsettled question, but one analysis by Barcelo, Finazzi, and Liberati in 2009 suggested something alarming. Within a superluminal bubble, vacuum fluctuations would generate intense Hawking radiation, the same type of radiation black holes emit at their horizons. Rather than serene darkness, the interior might heat up with a flood of high-energy particles. This Hawking-like radiation could roast anything inside, making a faster-than-light warp bubble a death trap unless new physics intervenes. This finding implies a fundamental limit. Go too fast with warp, and quantum effects light a lethal fire around you. However, they also noted that if the warp bubble stays subluminal, slower than light, these problems disappear. Below light speed, no true horizon forms. Information isn't completely walled off, and the Hawking radiation issue vanishes. It's a relief in one sense. A slow warp bubble might be safe and stable. Of course, a slow warp drive might seem to defeat the purpose. If it can't exceed light speed, why use warp at all? We'll return to that idea, because even subluminal warp travel could have its own advantages. But it underscores the strange truth. A warp bubble might have a speed limit of its own, not because of relativity this time, but because of quantum physics and stability concerns. So, inside our hypothetical warp bubble, the ride could either be uneventful or extraordinarily hazardous, depending on how fast we push it. Let's assume we're operating in a regime that's safe, perhaps at moderately relativistic speeds, or that future engineering has found a way around the Hawking radiation issue. In that case, the passengers experience weightlessness or normal shipboard gravity, if the ship has artificial gravity or spin for comfort. And they wouldn't feel the bubble's motion. They might gaze out a window and see an uncanny sphere of distorted starlight encircling them. Maybe a bright ring around a dark center, as light from the sides gets bent while light directly ahead can't reach them. Time would pass normally on board. If they play cards for an hour, they've aged an hour. Meanwhile, an observer back on Earth might calculate that the ship has covered trillions of kilometers in that hour, seemingly a physical impossibility, yet the ship's crew just calmly had their coffee break through it all. In the grand scheme, this is perhaps warp drive's most seductive promise. A journey that for the travelers is tranquil and swift, skipping the usual ordeals of acceleration and time dilation. It sounds almost too good to be true, and indeed, at our current understanding, it is. To make this gentle ride a reality, one must solve the tremendous engineering and physics problems that lie beneath that serene bubble surface. We need to figure out how to fuel and generate the warp bubble, how to navigate it, and how to avoid wrecking the destination upon arrival. Each of those challenges is a towering mountain in its own right. Let's begin with the question of fuel. What kind of energy could create a space-time wave big enough to carry a starship, and how much of it would we need? The original Alcubierre calculations were eye-opening in this regard. They indicated that the energy requirements for a warp bubble were astronomically large, far beyond anything humanity could muster. To create a bubble even a few hundred meters across, big enough to encompass a ship, you'd need negative energy on a mass-energy scale comparable to the mass of the planet Jupiter, or even more. In fact, an early estimate suggested a warp bubble wall might require a total energy equivalent to the mass of the observable universe, an absurd figure that underscores how exotic this concept is. Moreover, that energy would have to be in the negative form, something we don't know how to accumulate in bulk. The bubble's walls, the boundary between warped and unwarped space, would have to be incredibly thin, on the order of 10 to the negative 32nd meters or so, near the Planck length, to have the desired effect. Squeezing a universe's worth of exotic matter into such a razor-thin band of space is beyond impractical. It verges on the absurd. These daunting numbers led many physicists to conclude that warp drive, while fun to play with on paper, would likely remain fiction in practice. However, not everyone was ready to give up. The question became, can we tweak the design to lower that energy bill? Over the years since 1994, several researchers have proposed modifications to the warp concept that might reduce the exotic energy needed, or even in some cases, eliminate the need for negative energy entirely, with a trade-off that the drive can't go FTL. One of the first significant refinements came from physicist Chris van den Broek in 1999. He reasoned that Alcubierre's original bubble was perhaps wasteful in how it warped space. The bubble enclosed a fairly large volume of flat space for the ship, and its walls were thick. Van den Broek proposed a clever adjustment. What if you make the internal volume of the bubble larger, but the outside surface of the bubble extremely small? In other words, create a tiny neck or entrance to the bubble, and then a ballooned interior where the ship sits, a bit like a genie bottle shape in space-time. This pocket warp geometry meant that from the outside, the disturbance to space-time is very small, so it might require far less energy, while inside, there's enough room for the ship. His calculations showed that, theoretically, the exotic mass needed could be drastically reduced. Instead of needing universe mass, you might need something like the mass of a star or a planet converted to negative energy, still enormous, but a lot less ridiculous than before. However, there were catches. The space-time curvature near that tiny neck would be extremely intense, near the limits of quantum gravity, and the structure would be only a few orders of magnitude above the Planck scale. Building or maintaining such a bottleneck bubble might be just as infeasible as the original scheme, and the energy, while reduced, was still beyond anything short of Kardashev, Type 2 or 3 civilization, those who harness the power of entire stars or galaxies. Van den Broek's idea showed that improvements were possible in principle, but it didn't bring warp drive into the realm of the achievable. Not yet. Another approach was introduced by José Notario in 2002. Instead of focusing on energy requirements, Notario looked at the warp metric itself. He demonstrated that the defining feature of a warp drive, moving a bubble of space, didn't actually require having an expanding region behind and contracting region ahead, as Alcubierre had chosen. Alcubierre's particular solution had that structure, but Notario constructed a different solution where space wasn't expanding or contracting in the same way, yet it still constituted a moving warp bubble. In essence, he proved there are multiple ways to warp space-time for propulsion. The significance of this is partly conceptual. It means warp drive isn't a single unique metric but a family of possibilities, some of which might have friendlier properties. Netario's warp drive had no expansion of space at the back, hence he dubbed it warp drive with zero expansion. The details are highly technical, but this at least broadened the search space for a viable design. Perhaps a different warp metric could lower energy demands or avoid some of the nastier side effects. However, Netario's solution still required exotic matter. It was not a free lunch on that front. The hunt continued for configurations that could be more physically reasonable. In 2012, Harold Sonny White of NASA's EagleWorks lab made headlines by suggesting another modification to reduce the energy problem. White revisited Alcubierre's equations and found that by changing the geometry of the warp bubble, specifically by making the bubble's wall thicker and oscillating the energy intensity over time, one could greatly lower the peak energy needed. Instead of an extremely thin, high-density shell of negative energy, his concept used a somewhat thicker shell with a fluctuating field. This spreads out the energy and, counterintuitively, reduces the total exotic energy requirement. White claimed that with these tweaks, the amount of negative mass energy required could drop from something like a planet Jupiter's worth to on the order of a few hundred kilograms. In one optimistic assessment, he noted the requirement might be as low as the mass energy of the Voyager 1 space probe, approximately 700 kilograms. That's a mind-boggling reduction, from astronomical to merely heroic. If true, it would bring warp drive from utterly impossible to maybe, just maybe, within the outer bounds of human engineering in the far future. However, this proposal too comes with caveats. By thickening the bubble's wall, White's design shrinks the space available inside the bubble. Essentially, the ship would have to be much smaller to fit in the flatter central region. The warp bubble becomes less like a roomy sphere and more like a tight-fitting halo around a tiny craft. There's also skepticism in the physics community about whether these calculations truly hold up. Miguel Alcubierre himself expressed doubt, gently saying that from his understanding, there is no way it can be done, probably not for centuries if at all, when referring to claims of dramatically lowered energy requirements. In science, extraordinary claims require extraordinary evidence, and at this stage, White's ideas remain theoretical adjustments, not proven breakthroughs. Still, the door was open a crack. Perhaps warp drive didn't demand an entire planet of exotic matter. Perhaps clever engineering could chip it down further. And indeed, 21st century physicists have kept chipping away. Just a few years ago, in 2021, physicist Eric Lentz put forward a new class of warp drive solutions that intriguingly might use no negative energy at all. Lentz proposed a mechanism involving what are called solitons, stable, self-reinforcing waves that could form a warp bubble using only positive energy sources. This would be revolutionary, since the need for negative energy has been the biggest roadblock. However, the initial excitement was tempered by scrutiny from other experts. Critics pointed out that even Lentz's positive energy bubble, while mathematically derived, might in practice violate certain energy conditions, deep principles in relativity that prevent things like free energy or causality violations. In other words, some argue that any physically realistic warp drive, Lentz's version included, must still summon something exotic or break something subtle in the energy bookkeeping of the universe. The debate is ongoing, but it highlights how active this field has become. What was once a single far-fetched idea has blossomed into a small cottage industry of theoretical physics, with multiple teams trying to imagine better warp drives, ones that maybe we could actually build someday. Another notable development in 2021 was work by Alexei Bobrik and Gianni Martire, who developed a general model of warp drives and found that subluminal, slower than light, warp configurations could exist that use purely normal matter and energy. Essentially, They argued that if you don't insist on going faster than light, you can have a warp bubble solution that doesn't require negative energy at all, just incredibly dense positive energy. They even managed to optimize the original Alcubierre warp metric and cut down the negative energy needed by orders of magnitude. The catch? Their feasible physical warp drive would not exceed light speed. It could perhaps approach it, though, and it still wasn't something you could build with today's technology. For instance, one might need to compress a planet-sized mass into a shell around your ship to create the necessary distortion. That's hardly practical, but it's a far cry from needing more mass than exists in the visible universe. Slowly, step by step, the theory is inching towards something less impossible. In summary, fueling a warp drive remains a tremendous challenge. The classic design wants negative energy, a substance we're not sure how to produce in bulk, and in ridiculous amounts. Various refinements, Van den Broek's bubble, Notario's alternate metric, White's oscillating torus, Lenz's soliton, Bobrick and Martyre's models, have whittled down the requirements or offered alternatives, but none have put warp drive in the realm of easy engineering. The most optimistic scenarios still involve manipulating stupendous energies and possibly new states of matter. If a warp drive is ever built, it might run on exotic physics, akin to harnessing dark energy or the vacuum itself. Perhaps future generations will unlock quantum gravity or vacuum energy extraction to supply what's needed. As of now, we can outline the theory and sketch out the improvements, but we don't have the fuel to get started. However, let's suppose that one day we solve the energy puzzle. Imagine we have the means to generate a warp bubble. The next question is, how do we use it? How do we form that bubble around a ship, navigate it to a target, and then safely turn it off when we arrive? The operational aspects of a warp drive are just as mind-bending as the bubble itself. Creating a warp bubble in practice might involve first assembling the strange energy distribution required. Some proposals suggest placing rings or donuts of intense energy around a craft to induce the warp field. Perhaps a futuristic ship would deploy a ring of plasma or a belt of negative energy generating devices that encircle it. In many illustrations, warp ships are shown with large circular structures, inspired by the original Alcubierre paper's diagrams. These could be warp field coils that shape the bubble. But however it's done, the key is that the space-time shape must be established. One big complication. As noted earlier, you can't form a bubble out of nowhere at superluminal speeds. One idea forwarded by physicist Sergei Krasnikov was that if you can't instantly form a bubble, maybe you can prepare the path instead. He imagined a kind of permanent tunnel in space-time, formed by sending a vehicle to a destination at sublight speed while creating a distortion behind it. This would leave a sort of tube, connecting 2 points, through which later travelers could zoom FTL, a concept now known as the Krasnikov tube. Think of it as laying down a deformable conduit through space on a one-way trip, then using that conduit for a nearly instantaneous return journey. It's a bit like hauling one end of a wormhole to the far star and then having a shortcut back. The downside: the first journey still takes the long, conventional duration. You can't shortcut a truly new destination. And each tube only connects specific points. It's an intriguing hybrid between warp drive and wormhole ideas, essentially building a network of space-time railways. But crucially, even the Krasnikov tube demands exotic phenomena and extreme energy, much like warp bubbles. It doesn't circumvent the fundamental energy challenge. It just reorganizes it. Also, as other researchers like Glenn Cool have argued, using these schemes might require having a warp drive to start with, a paradoxical requirement that limits their practicality. Nevertheless, It paints a picture of a possible future, one where we gradually establish corridors or highways in space-time between important systems. The first ship voyages slowly, constructing the route, and thereafter the distance is effectively shortened for everyone who follows. If instead we focus on a single ship's capability, forming its own bubble when and where it likes, we confront the navigation problem. Let's say our ship can generate a warp field. How do we aim and control it? The straightforward answer is that it might be largely pre-programmed. Because no signal can outrun the bubble from within, the ship's computer would need to calculate the bubble's trajectory and duration beforehand. The crew would input their destination and perhaps set a course, then engage the drive. The warp bubble would envelop the craft and detach from the starting location, moving on whatever trajectory was set, much like a thrown spear. During the superluminal cruise, course corrections might not be possible unless some portion of the bubble can be influenced by external forces or fields. Perhaps advanced warp drives could modulate the bubble shape asymmetrically to allow gentle turns or adjustments, but this is speculative. One could imagine a network of navigational beacons or gravitational markers that a warp bubble automatically locks onto, guiding it along safe lanes through the galaxy. Alternatively, warp travel might be done in shorter hops, rather than one continuous burn. Exit the bubble periodically to get bearings and then re-engage for the next leg. This could mitigate the blindness of being in a warp bubble. It's analogous to a submarine surfacing occasionally to check its position, because deep underwater it can't use GPS. A warp ship might need to drop out of warp between stars, orient itself, then continue. Starting the bubble could be as dramatic as it sounds. Perhaps the ship's warp coils spin up with a rising hum. Exotic particles are funneled around the hull, and suddenly, space-time breaks free from the bounds of normal geometry. To an external observer, there might be a burst of radiation or a sudden distortion around the craft as the bubble forms. Some studies even liken the bubble formation to a burst of Cherenkov radiation, the blue glow of particles exceeding light speed in a medium. The idea being that as the bubble accelerates from subluminal to superluminal, it might shed a shock of energy. This is speculative, but it emphasizes that starting and stopping a warp bubble likely won't be subtle events. They could be energetic and potentially hazardous if done near other objects. For this reason, one can envision strict protocols. For instance, a ship must move to a safe distance from any space station or planet before engaging its warp drive to avoid blasting nearby structures with the startup effects. Similarly, when arriving, it should decelerate well away from inhabited areas. We'll delve into the arrival issues shortly, but clearly the act of initiating or terminating faster than light travel has to be handled with care. Steering a warp bubble once en route remains a puzzling issue. Notario's critique stands. Inside a classic warp bubble, you are a bit helpless. However, perhaps the bubble could be designed to be responsive in some way. One idea is that if you have some normal, sublight propulsion, or the ability to emit energy within the bubble, you could shift your position slightly, and the bubble might follow the center of mass. Another is that if part of the warp field extends ahead of the bubble, one might modulate that extension via some quantum effect or a layered field. These ideas go beyond what the original equations considered. It may be that a real controllable warp drive would need a more complex structure than the simple one Alcubierre wrote down, something with multiple field layers or a feedback mechanism allowing the bubble to be tugged or tilted from inside. In absence of those ideas, the safe bet is that navigation will rely heavily on planning. A warp bubble might be fired like a bullet. You better be pointed the right way at launch. Astronautics might revert in some sense to the age of ballistic trajectories. precise calculations ensuring that when you pop out of warp, you're near where you intended. There's little room for error when your mid-course correction options are limited. Finally, stopping the warp bubble is its own delicate matter. In theory, to decelerate from superluminal speeds, one must turn off the field gradually. If the bubble simply collapses all at once, while moving faster than light, relative to the destination, all the energy and particles trapped around it will be released abruptly. Research by Brendan McMonagle, Geraint Lewis, and Philip O'Byrne highlighted a grim scenario. As the ship decelerates out of warp, the pocket of space it carries would disgorge a blast of whatever it accumulated en route: radiation, interstellar medium particles, all compressed and blue-shifted to extreme energies. It's akin to what happens at the inner horizon of a rotating black hole, where infalling light can blue-shift indefinitely. The calculations showed the forward-facing release could be energetic enough to destroy anything at the destination straight ahead. In plainer terms, arriving from warp could be like detonating a massive bomb at your arrival point if you're not careful. Clearly, this is not what we want for a happy landing. The implication is that a warp drive must have a controlled shutdown. Instead of slamming the brakes, one might gradually ease out of warp, dissipating the energy over a longer distance or time. For instance, a ship could begin to slow its bubble while still in interstellar space, far from planets or stations, letting the high-energy build-up radiate into the void. By the time the ship actually comes out of warp near its target, the hazardous shock has been largely released or reduced to harmless levels. There might also be shielding fields or clever channeling of particles built into advanced warp drives, perhaps a way to vent the energy in a safe direction. One concept suggests angling the warp bubble so that most of the dangerous radiation is directed away from the destination, like a flashlight beam you aim aside, then turning off the bubble. Future engineers might design warp fields that naturally shed accumulated particles out the back during flight, instead of letting them pile up at the front. Van den Broek's modification, interestingly, might help here. A very small front cross-section for the bubble means it sweeps up less matter and may avoid a large dangerous build-up. In fact, that earlier study noted the horizon problem, meaning the disconnection and associated Hawking radiation might be eliminated in the Brock metric, potentially meaning a safer, more permeable bubble. If true, such refinements could solve multiple issues at once, making warp bubbles that are easier to start, easier to stop, and won't incinerate whatever they're pointed at when they arrive. The arrival hazards of warp travel underscore a general theme. Any technology that bends the rules so profoundly will have equally profound side effects to manage. A starship captain in the age of warp drives might have to think as much about shockwaves and radiation cones as about fuel and cargo. Perhaps approaching a planet at warp speed would be absolutely forbidden. Instead, ships might emerge from warp at the edge of a solar system and then proceed inward at conventional speeds, both for safety and courtesy. One can imagine traffic control for warp ships. Designated emergence zones far from inhabited worlds, where any burst of exotic radiation will dissipate harmlessly in space. Over time, if warp travel becomes routine, there could be established slow-down lanes, regions where ships know to start breaking their warp bubble in advance. These might even be augmented by infrastructure, maybe satellites that help bleed off the warp field energy as a ship arrives, like tugboats guiding in a speeding vessel and absorbing its wake. All these ideas are speculative, of course, but they arise naturally from asking, what happens when you stop? It's not enough to get somewhere quickly. You have to do so without blasting your destination to bits. Now, considering all these technical and safety issues with faster-than-light warping, some scientists have proposed a compromise. What if we don't push for FTL right away? What if we use warp field technology to achieve high subluminal speeds, which are still extraordinarily useful, and avoid the nastier problems? A subluminal warp drive might sound like an oxymoron. Why use a warp drive if not to go faster than light? But it could confer significant advantages. For one, as noted earlier, a subluminal bubble shouldn't create an event horizon or Hawking radiation heat, making it likely much easier to manage and survive. It would essentially act as an inertialess drive. The ship could accelerate to, say, 0.5 c or 0.8 c extremely quickly without internal g-forces, because the warp field pushes space around it instead of pushing the ship through space. This could cut down travel times to nearby planets, or even nearby stars dramatically, without breaking the light speed barrier. Imagine reaching Mars in minutes, or a nearby star in a few years instead of decades. All the while you feel nothing but calm on board. You'd still be bound by relativity's speed limit, so a round trip to a star would take years, and time dilation would still occur for those outside the bubble. The cruise time might remain normal, but observers would see their clocks slow if they approach light speed. However, because the crew isn't accelerating through space-time in the usual way, perhaps the time dilation effects could be mitigated or controlled by how the bubble interacts with external frames. There's ongoing research into these questions. Crucially, subluminal warp drives may be physically plausible with known physics. Bobrick and Martyr's work in 2021 explicitly showed that slower-than-light warp spacetimes can be constructed with purely positive energy. In their framework, you could, in principle, build a warp-like propulsion system that doesn't require exotic matter, as long as you're content to stay under light speed. Such a system might still need ultra-dense mass or advanced technology, for example, compressing a huge mass into a small volume to curve space. But it doesn't ask for new physics. This is a huge conceptual shift. It means warp field technology might first appear not as a means to instantly pop over to Alpha Centauri, but perhaps as a revolutionary Earth-Mars transit system, or a way to send probes at, say, 0.1 c with no propellant. Think of it as the warp drive as a boost to conventional travel, eliminating the acceleration limits and maybe drastically cutting travel time without invoking the full Cinderella magic of FTL. The idea of slow warp may also lend itself more readily to experimentation. If we don't have to break light speed, we might attempt to create tiny warp bubbles in the lab as a demonstration of the effect. In fact, lab experiments have been and are being attempted. Harold White's team, when at NASA Eagleworks, set up an interferometer experiment to detect minute spatial distortions that a small test warp field might create. They used what's called a White-Juday warp field interferometer, which would show a slight change in the path length of a laser beam if a warp field is generated in one arm of the device. Initial tests around 2013 were inconclusive. No clear warp signature was seen, which wasn't too surprising given the extremely subtle effect they were seeking. But these efforts signaled that warp research was moving from pure theory to at least the fringes of experiment. More recently, in 2021, White, who had moved on to the Limitless Space Institute, and colleagues reported something extraordinary. They claimed to have identified a real, albeit tiny, warp bubble in a nanoscale experiment. While studying Casimir cavities, tiny structures that produce negative energy densities between their plates, they found a particular configuration that the calculations said would produce the exact energy distribution of an Alcubierre warp bubble on the microscale. In essence, a little warp bubble might have briefly emerged in the lab, not big enough to do any travel, but as a proof of concept of the space-time geometry. White described it as a real, albeit humble and tiny, warp bubble. This result is still very fresh and being vetted by the scientific community, but if confirmed, it would be the first physical manifestation of warp physics. Such a micro-warp bubble would be trillions of times too small to carry anything, but it's akin to creating the first spark of fire in a world that's never seen flame. It shows that the exotic fields needed might be arranged, in principle. From there, one would try to scale up, perhaps millimeter-sized warps, then meter-sized. Decades or centuries of development could stand between a nanobubble and a starship, but every journey begins with a small step. We also see interest from independent and academic researchers in designing what we might call warp prototypes. These are theoretical designs for devices or experiments that mimic aspects of a warp drive on a small scale. For instance, some have proposed using metamaterials or special energy configurations to simulate the effect of contracting space on one side of an object and expanding it on the other, just by a tiny amount. Others examine analog systems, for example, using sonic waves in a medium or circulating laser beams to create something mathematically analogous to a warp bubble, to test how it behaves. While these aren't warp drives in the sense of propelling a ship, they teach us about the underlying physics. The hope is that as we learn to manipulate space-time in small ways, we'll progress toward larger effects. Just as early experiments with electromagnetism eventually led to electric power and radio transmission, these baby steps in space-time engineering might one day culminate in the real warp drives of science fiction. At the same time, alternative, faster-than-light concepts continue to be explored, often overlapping with warp ideas. One such concept is the Krasnikov tube we touched on, essentially a fixed distortion or tunnel through space. Another is the notion of a traversable wormhole, which in some respects is like a warp drive that creates a permanent shortcut rather than moving a bubble. Wormholes also require negative energy to hold them open. And there's intriguing theoretical work on whether a warp bubble could be turned inside out to create a wormhole mouth. Imagine flying your warp bubble to a distant location and then inflating it into a stable wormhole entrance. You'd effectively plant a doorway for instantaneous travel between the start and end points. This would marry the mobility of warp drive with the station-to-station convenience of wormholes. It's a highly speculative idea, but it shows how these exotic concepts might interact. If one had mastery over space-time, one could deploy whichever tool best suited the need. A moving bubble for exploration, a stationary tunnel for infrastructure. Perhaps future engineers would even create warp gates, devices that generate a warp bubble around incoming ships and guide them, functioning like an FTL traffic control. These would be a bit like the relay stations or jump gates imagined in various science fiction universes, where you enter the gate and it warps you to another connected gate. In such scenarios, individual ships might not need to carry powerful warp drives. Instead, massive installations provide the required energy and stabilization to send ships across space. That could be more efficient and safer, albeit less flexible, than every vessel bending space-time on its own. Considering the possibilities, one can envision a network of cosmic highways emerging. In the far future, if humanity, or any spacefaring civilization, cracks the code of FTL travel, they likely won't do so in isolation. They will build routes, hubs, and nodes, an interstellar transportation network, Krasnikov tubes linking major colonies, warp gates at hub stars, perhaps even wormholes for instantaneous jumps, all knitted together. Travel could become a sequence of jumps and bubbles. You warp to a transfer point, slide through a wormhole to another galaxy, then warp again to a specific destination. The cosmic highways might literally reshape civilizations, enabling commerce, tourism, and migration across what were once unfathomable gulfs. Yet these highways might also be selective. Maybe only certain well-resourced sectors get them. there's an implicit potential for inequality. The core worlds with their maintained space-time routes prosper, while frontier worlds without such links remain isolated. If history is any guide, infrastructure tends to concentrate wealth and influence. The first nations to build railroads or air travel networks gained huge advantages. Imagine the stakes when the infrastructure is a set of FTL corridors spanning star systems. This brings us to the final consideration we must not ignore: the ethical, societal, and environmental implications of opening these cosmic highways. The ethics of faster-than-light travel might not be immediately obvious. After all, if it becomes possible, isn't it just a great boon? But transformative technologies have always come with profound questions, and warp drives or wormholes would be no exception. First, there's the issue of equity. Who gets to use this technology? If developing a warp drive requires enormous energy and expense, it might be initially limited to wealthy nations, private corporations, or military forces. A gap could emerge between those who have access to near-instant travel and those who don't. Entire planets or societies might be left behind, economically and culturally, if they're not part of the FTL network. On Earth, we've seen how the digital divide, or disparities in transportation access, can exacerbate inequality. On a galactic scale, the difference could be far more dramatic. It leads to the question: should warp technology, if achievable, be shared openly for the benefit of all, or will it be guarded and monopolized? One can hope for a Star Trek-like scenario where humanity unites and the warp drive becomes a common heritage. But our history often shows otherwise. The prospect of some faction controlling rapid transit among the stars might lead to tensions or even conflict. And what about safety and demilitarization? A warp drive isn't just a fast engine. It's also potentially a formidable weapon, or at least a cause of destruction if mishandled. We discussed how a ship emerging from warp can release deadly energies. In hostile hands, one could deliberately drop out of warp near an enemy planet and inflict catastrophic damage without ever firing a traditional weapon. The warp bubble itself could be the weapon. Even the ability to appear anywhere with no warning gives a massive strategic advantage. Much like the advent of stealth aircraft, or ICBMs, changed warfare on Earth, FTL could render distance and borders meaningless. A warship could warp into orbit above a city with little to no forewarning. This raises the spectre of an arms race in FTL technology. It may become imperative, as soon as one party develops it, for others to follow, or to develop countermeasures, perhaps some way to detect or destabilize a warp bubble. The international community might attempt to regulate it, akin to how we have treaties for nuclear weapons and rules for space. We might see agreements that no one will emerge from warp within a certain proximity of inhabited planets, or even bans on militarizing warp travel, though enforcing such rules could be tricky. The early uses of warp might indeed be military or exploratory, as those often receive funding first. Ensuring this capability doesn't lead to domination or devastation will be a major ethical and political challenge. Another angle is the stewardship of space-time itself. This is a new concept we haven't had to worry about before. Human industry has taught us hard lessons about environmental stewardship. We learned that polluting the air and water can have global consequences. With warp drives, our environment extends to the fabric of space and time. We have to consider: does warping space-time leave a trace? Could it have cumulative effects? For instance, if many warp bubbles are zipping around a region of space, do they leave residual gravitational disturbances or radiation fields? Might the fabric of space-time develop fatigue or anomalies from overuse, akin to wear and tear? Some theorists have speculated about vacuum decay or other catastrophic events that might, very, very unlikely, be triggered by extreme manipulations of space-time. While these are far-fetched, the basic idea of being careful with space-time is sound. We'd be unleashing energies on scales rivaling stars, since bending space significantly is no small feat. If not managed properly, we could inadvertently damage the very medium we're traveling through. It sounds odd to say polluting space, but one could imagine, for example, a poorly designed warp drive creating high levels of dangerous radiation along its path, rendering some corridors hazardous for others to use until it dissipates. There's even the frightening thought of causality violations. If warp drives allow any form of backward time travel under certain conditions, one might create paradoxes or timeline issues that could have existential consequences. Thankfully, it seems likely that the laws of physics themselves prevent the worst of those, via mechanisms like Hawking's chronology protection, conjecture, which would cause a time-looping warp configuration to self-destruct in a burst of energy. Even so, it reinforces the point. Playing with FTL is playing with fundamental forces that we are only beginning to understand. Proceeding with caution will be crucial. Societally, the introduction of warp capability would be as paradigm-shifting as the discovery of fire or electricity. Perhaps even more so, because it literally changes humanity's relationship with distance and time. Cultures might need to adapt to a universe where distance is no barrier. We could see a unification of distant colonies, or the emergence of new cultural blends as travel times shrink. But we could also see a form of cultural shock, what some have termed the galactic shock, analogous to future shock, where the pace of expansion and change overwhelms individuals and institutions. Entire new industries and dangers would arise, from FTL shipping to perhaps space-time smuggling. Imagine someone warping forbidden materials, or even people across borders easily. Law, ethics, and philosophy will race to catch up. Do you allow anyone to just warp anywhere, or are there designated lanes? How do you police something that can appear and disappear across light years? These questions highlight that the technical challenge, as immense as it is, might be only half the story. The other half is ensuring that once the cosmic highways open, we travel them responsibly. As we conclude this exploration of warp drives, it's clear that what began as a fanciful idea has evolved into a rich domain of scientific inquiry. The vision of a warp-speed starship, slipping quietly through a self-made ripple in space, captures our imagination like few other things. It speaks to a deep yearning to cross the vast ocean of stars, not as a centuries-long voyage, but as a manageable journey, perhaps even a wondrous cruise through distorted starlight. In pursuing that dream, we have pushed our understanding of physics to the edges. We've confronted the strange requirements of negative energy. We've stumbled upon connections to quantum theory and black hole physics, and we've had to broaden our conception of what travel means. Every answer uncovers new questions. We solved, on paper, the riddle of superluminal travel without relativity breaking, only to find practical barriers that demand new science. We find hints that the universe might allow these cosmic shortcuts, but only with safeguards, like enormous energy tolls or built-in instability if, misused, that compel us to grow in knowledge before we can use them. It may be that these safeguards are telling us something, that wielding such power requires wisdom and care commensurate with its scale. Standing here, metaphorically, at the threshold of the stars, we are both exhilarated and humbled. Wormholes and warp drives offer us cosmic highways, but not without cost or challenge. As we contemplate building them, We also must decide how to regulate them, how to share them, and how to prevent their misuse. It's a future problem that we might be fortunate to face, because it means we've advanced far enough to actually travel out among those distant lights in the sky. The road from Alcubierre's 1994 paper to a functioning warp drive might be long. It could take decades, centuries, or longer. Or it might surprise us and happen sooner than most expect, with an unforeseen breakthrough. Either way, the journey of understanding is well underway. Bit by bit, experiment by experiment, we're peeling back the layers of possibility. In the quiet of a spacecraft cabin, a future traveler might one day unbuckle and float to a window. Outside, nothing looks familiar. A distortion, a deep darkness, maybe a shimmer at the bubble's edge. They know that just beyond that invisible wall, space is rushing by faster than light, stars warping from ahead to behind in the blink of an eye. Yet inside, it's calm. The traveler feels a pang of awe and responsibility. In their hands, or rather, in their ship's engines, lies the power to reshape reality for a little while, to fold the fabric of the cosmos. It's a privilege earned by a civilization that dared to dream and to learn the universe's secrets. As that ship prepares to slow and emerge into the starlight of a new world, perhaps the traveller takes a deep breath, knowing the energies at play and the precautions taken to protect their destination. The bubble will dissipate, the strange ride will end, and normal space will welcome them back. And when it does, they'll carry with them not just their personal hopes, but the collective hope of all those who yearn to reach across the gulf of space, carefully, wondrously, and with eyes open to both the marvels and the responsibilities of these cosmic highways. The voyage continues, and with each step, we learn how to navigate not just the stars, but the very fabric of space and time itself. Time can be a slippery thing when we push the limits of speed. Imagine drifting in the silent darkness between stars, watching clocks that no longer agree. When one moves near light speed, the very idea of now begins to blur and bend. A moment that feels simultaneous to you might not be to someone racing in another direction. Reality holds no single, universal ticking clock. Each traveller carries their own time, and those times can fall out of sync in the strangest ways. In this delicate dance of clocks and perspectives, faster-than-light travel introduces a peculiar twist. Suppose an explorer could somehow leap across light years in an instant, outrunning even the beams of starlight that normally mark time's limits. To the traveller, it might feel like a miraculous jump forward. But to another observer drifting elsewhere, that same jump could look oddly out of order. Effects preceding causes, arrivals before departures. Two observers, moving differently, might even disagree on which event came first. This isn't a trick of perception. It's woven into the fabric of space and time. Albert Einstein's relativity taught us that simultaneity, the very notion of things happening at the same time, is relative. If I glide past you on a starship at immense speed, the events I call simultaneous won't match the ones you do. For you, my journey might unfold in a straightforward sequence: departure, then arrival. But for me, or someone in motion differently, those events could swap or overlap in surprising ways. Now add a dash of impossibility. Let's grant our starship an ability to jump faster than light. Picture the explorer leaving Earth in a flash, bound for a distant world. To mission control on Earth, perhaps they see the ship vanish, and then, moments later, detect its arrival at a far-off star. But imagine a second observer, a scout ship, moving at high speed relative to Earth. In the scout's eyes, the timing skews. They might witness the far-off arrival first, and only afterwards see the ship depart Earth. From that perspective, the traveller seems to appear at the destination before they ever left home. What mischief lurks in such scenarios? If information or messages ride along these faster-than-light jumps, they can become unwitting time messengers. A simple hello, sent faster than light, could loop around and arrive in the sender's own past. Think of sending a birthday wish to a friend on a spaceship across the galaxy via an FTL signal. In one frame of reference, the greeting arrives after it was sent. Perfectly normal. But in another frame, zooming through space, the same greeting might show up a day before it was even transmitted. Our friend could receive congratulations for a birthday that hasn't dawned yet in the sender's time. It gets stranger still. Imagine two adventurous souls, Alice and Bob, each with a faster-than-light communicator. Alice is on Earth, and Bob is on a fast-moving ship passing by. At a precise moment, from Earth's viewpoint, Alice impulsively sends Bob a superluminal message, perhaps a single ping of quantum code, just as Bob's ship flies past. Bob zips away, but being equally impulsive, replies instantly with his own FTL signal back to Alice. Here's the cosmic prank. Because Bob is moving relative to Alice, his notion of timing is skewed. His reply might head out when, by his clock, Alice hasn't even sent her original message yet. The result? Alice could receive Bob's response before she ever said hello. A reply without a query. An answer preceding the question. Such a situation defies our common sense. Cause and effect twist into a loop, raising the spectre of a temporal paradox. One could imagine Alice scratching her head, reading a message from Bob that says, "I got your hello, thanks," when she hasn't sent anything at all. Would she then decide to send the hello to fulfill the loop, or not send it, and leave the effect without a cause? The universe shudders at these paradoxical possibilities, as if warning us that something fundamental could break if we push too hard against the light-speed barrier. In truth, physics as we know it forbids these scenarios. Special relativity, the rulebook of high-speed motion, has a strict guideline. Nothing with mass can outrun light. But here on our hypothetical cosmic highway, we are entertaining the notion that perhaps some clever trick, like a warp drive or wormhole, might let us cheat that rule. The moment we allow that cheat, the rulebook fights back with these troubling time tricks. The cosmos offers a deal. Faster-than-light travel may be conceivable, but only if we accept that before and after are no longer simple, agreed-on truths. If one frame's faster becomes another frame's backward, we are treading into dangerous territory indeed. It's a reminder that even if we build engines to pierce the light speed limit, we cannot escape the interconnected tapestry of space and time. The warp drive might bend space, the wormhole might shortcut through hidden dimensions, but the background dance of clocks and causality still plays its tune. A ship that jumps the queue in space might also be cutting in line in time. And when faster starts to feel like earlier, when an arrival seems to precede its departure, we are forced to ask, have we opened the door to time travel by mistake? Such questions aren't just academic. They strike at the principle of causality, the rule that says causes happen before effects. Our whole understanding of physics, of reality, leans on that arrow of time. Break it, and you break the logical underpinnings of how events unfold. If faster-than-light travel allows messaging the past, then every journey could become a potential tangle of timelines. A simple trip could rewrite history or create contradictions, situations where something happens without a clear origin, or events occur that undo their own causes. To safeguard causality, some hidden enforcement might need to step in whenever we flirt with superluminal speeds. Perhaps Unbeknownst to us, nature has quiet fail-safes. Or perhaps any civilization that masters such travel must learn the rules of a larger game, a careful choreography to avoid cosmic confusion. Already, our minds may drift to a startling implication. What if by building a cosmic shortcut, we inadvertently construct a time machine? If a starship's leap can deliver messages into yesterday, could a round trip deliver a person to the day before? The idea that moving faster than light could turn into moving backward in time has long captivated and unsettled scientists and writers alike. It's as if the universe has a built-in alarm, ringing whenever we attempt to outrun light, cautioning that time itself is at stake. As we stand at this threshold of possibility, the air tingles with both excitement and trepidation. The dream of roaming the galaxy in hours or days comes entangled with the spectre of unintended time travel. It's a cosmic irony. The faster we seek to go, the more carefully we must tiptoe around the chronology we take for granted. And so, before leaping into those inviting wormholes or powering up warp drives, we pause to consider the paradoxes that might await. If our highways through the cosmos double as tunnels through time, what wonders or woes could emerge? Gazing into the starlit void, it becomes clear. Any venture beyond light's limit must confront these puzzles of time. Each potential solution seems to open new questions. Perhaps by exploring those questions, we inch closer to understanding how to travel fast, without unraveling cause and effect. In that spirit, we journey onward, deeper into the subtleties of time and space, searching for ways to navigate the cosmic highways while keeping history intact. The notion of a loop in time is both enchanting and unsettling. Picture tracing a journey through space that somehow circles back and delivers you to the very moment you began. In this bizarre pilgrimage, yesterday and today touch, forming a closed loop in the fabric of space-time. Physicists have a name for such a path, a closed, time-like curve, essentially a route through the cosmos that brings you back to your own past. While it sounds like pure fantasy, general relativity, Einstein's grand design of gravity and space-time, leaves a door ajar for such loops under extraordinary circumstances. Over the years, scientists have dreamed up various exotic mechanisms that might twist time into a circle. One of the earliest glimpses of a time loop came from pondering something as simple as a rotating mass. Not a spinning top or a planet, but a colossal, near infinite cylinder whirling end over end in space. Imagine an object like a giant ring or tube, so long it stretches beyond the horizon, and set it spinning at near light speeds. Around such a fantastical structure, space and time themselves would get dragged along in the rotation. If you flew a spaceship in the direction of the spin, the swirling space-time might tug you in peculiar ways. Physicist Frank Tipler analyzed this idea and found that an infinitely long, fast-rotating cylinder could, in theory, twist time into a loop. A ship, following a precise spiral around the cylinder, might find that instead of merely completing a circle in space, it also circles back in time, ending up at an earlier, when even as it returns to the same where. This remarkable possibility opened physicists' eyes to time travel as a serious, if speculative, solution of general relativity. Still, the Tipler cylinder remains purely hypothetical, demanding extreme conditions beyond plausibility. Of course, a Tipler cylinder remains a thought experiment's delight. It calls for either a truly infinite object or one made of impossibly dense, exotic material to work in a finite size. No one expects to stumble on an infinite spinning tube in the real cosmos. But its legacy is profound. It showed that Einstein's equations don't slam the door entirely on time travel. The rotating cylinder is like a signpost, pointing into a foggy domain of space-time where our intuition fails. It whispers that if gravity and motion are arranged just so, they might forge a pathway to the past. Rotation, it turns out, is a recurring theme in these time loop tales. Even nature's most fearsome whirl, the rotating black hole, hints at strange temporal gymnastics. Deep within a rapidly spinning black hole, if one were bold or foolish enough to venture inside, the mathematics suggests time and space might swap roles, and paths could, in principle, loop back on themselves. The core of a spinning black hole, often envisioned as a ring-like singularity, could be a gateway not just to elsewheres, but to elsewhens. Legends of physics tell of trajectories threading through that ring and emerging perhaps in another time or universe. Yet, for all its allure, that inner sanctum remains behind an event horizon, sealed away. If any time loops lurk there, they're tucked safely out of reach, imprisoned by gravity's ultimate one-way door. In essence, nature hides this potential time-twisting trick deep inside a place we cannot access. A rotating black hole may tease time travel, but it keeps the secret well guarded. If nature doesn't readily offer accessible time loops, might we craft one ourselves with advanced technology? This leads us to the idea of wormholes, the hypothetical tunnels through space-time connecting distant points. By themselves, a wormhole can be a bridge to far-flung corners of the universe. But if one end of the wormhole experiences time differently than the other, that bridge can become a loop in time. Here's the recipe. Take a traversable wormhole and set its two mouths in motion relative to each other. Perhaps you leave one mouth near Earth and load the other onto a fast-moving starship. Fly that ship on a high-speed round trip, maybe close to the speed of light or orbiting near a massive star, and then bring it back. Due to the strange alchemy of time dilation, the travelling mouth returns younger than its stay-at-home twin. In effect, one mouth lags behind the other in time, like two clocks out of sync. Now, a curious opportunity arises. If you enter the younger mouth, the one that took the trip, and pass through the wormhole, you'll emerge from the older mouth, which is anchored in an earlier time. To an outside observer, it looks as though you vanished into one mouth and popped out of the other before you went in. You could literally step into the wormhole and arrive in your own past. By walking through, you've leapt backward in time, courtesy of the time gap created between the wormhole's mouths. If you're not careful, you might even meet your younger self, who has yet to take that fateful step. The wormhole has become a time machine. This scenario was famously explored by physicists Kip Thorne and colleagues when they pondered whether a benevolent wormhole could be turned malevolent against causality. They realized that moving one mouth of a wormhole at high speed or parking it near a strong gravitational field effectively creates a time offset. When reunited, the two ends form what is essentially a loop in time waiting to be traced. Send a message through, and it could emerge in the past. Shine a flashlight into one mouth, and its beam might exit the other side before it ever left your hand, a shimmering ghost of illumination from yesterday. The implications were both thrilling and terrifying, implying that if wormholes exist and can be manipulated, our chronological safe house could be breached. Not to be outdone by wormholes or infinite cylinders, the cosmos offers another odd conduit for time loops: cosmic strings. These are hypothesized ultra-thin strands of energy, relics from the infant universe, as dense and massive as a billion suns, yet hair-thin. If such strings exist, they would be rifts of enormous gravitational pull stretching across space. Normally, a single static cosmic string, while exotic, wouldn't necessarily let you travel back in time. But consider two cosmic strings barreling past each other at immense speed, nearly the speed of light. As they streak by, their combined gravitational dance warps space-time in a peculiar way. J. Richard Gott, an astrophysicist, proposed that under just the right conditions, two passing cosmic strings could create a warping so severe that time loops become possible. Envision threading a spaceship through the moving cosmic strings at the opportune moment, like a nimble surfer catching a gravitational wave. If the geometry lines up, you might complete a circuit around the strings and find that you've arrived before your departure. In a universe crisscrossed by such strings, advanced navigators could perhaps hitch rides on these loops, like express trains that not only go somewhere, but some when. Once again, the practical challenges are astronomical. Cosmic strings, if they exist at all, might be vanishingly rare or far beyond our reach. And flying precisely around two of them in close encounter would be a navigational nightmare. Yet, the mere possibility adds to a striking pattern. General relativity seems to permit time machines of a sort, if one is clever and the universe obliges with the right materials. These closed, time-like curves, born from rotating rings, moving wormhole mouths, or the wild rush of cosmic strings, stretch our imagination. Each is like a loop in a tapestry, normally woven flat, that has been pulled and threaded back into an earlier weave. In those loops, cause and effect could become entangled. You might set out to explore the stars and accidentally find yourself colliding with history, perhaps even your own. It raises profound questions. If you can loop back and change something, will you or can you? Do these loops allow freedom to rewrite events, or do they simply make you an actor in an already written play, bound by what's happened? One proposal to resolve the potential paradoxes is the Novikov self-consistency principle. It gently suggests that if time loops exist, events will conspire in a self-consistent way. In a loop, you could not change history to create a contradiction. Any attempt to do so would somehow fizzle or end up causing the very outcome you were trying to prevent. In other words, you can travel back in time, but you can't change the past. You can only fulfill it. If you went through a wormhole to stop a disaster yesterday, you might find that your very presence was what set it in motion in the first place. The loop would close consistently, with no paradox. However, self-consistency is cold comfort if you're hoping to use a time loop for do-overs or world-altering interventions. And it remains a speculative idea, a possible rule the universe might enforce if causality is threatened, but nothing proven. Another possibility often floated in fiction is that a time traveler might slip into a parallel timeline, creating a new branch of reality while leaving the original timeline intact. Yet here too, we wander into realms beyond testable science. General relativity's loops don't come with an obvious user's manual on how paradoxes resolve. They simply show that the stage for such strange scenarios is not outright forbidden. As we contemplate these loops in time, a mix of awe and unease settles in. It's one thing to race along a cosmic highway faster than light. It's another to take an exit ramp that circles back to yesterday. The existence of even theoretical time loops means our universe's rulebook has more pages than we thought, some written in cryptic ink. They invite us to question whether causality is an absolute commandment or just a guideline that can be bent with clever engineering. But before we get carried away with visions of time-hopping adventures, we must consider whether the universe might have hidden mechanisms to prevent such causality violations. After all, just because the map shows a road doesn't mean the road is passable or safe. Could it be that some deeper law, some unseen pressure in the fabric of reality, steps in to block these loops from forming in practice? The next clues lie in the subtle whispers of quantum physics and the conjectures of cautious theorists, hinting that time machines, even if allowed in theory, might be snuffed out before they fully coalesce. If our cosmic imaginings have taught us anything, it's that nature often has subtle ways of enforcing its rules. Just when we think we've found a loophole, some deeper principle swoops in to stitch it closed. So it may be with time travel. After exploring how relativity might allow loops in time, physicists began to suspect that something unseen prevents those loops from ever becoming reality. The whisperings of the quantum world hinted at a kind of cosmic veto, a chronology protection agency, as Stephen Hawking whimsically called it, that safeguards the past from meddling by disallowing time machines. Hawking's hunch was more than just a flight of fancy. He and others dug into the equations of physics and found clues that whenever a time machine seems poised to form, quantum forces rise up like an immune response. Take the example of the wormhole time machine. As we saw, if you move one mouth of a wormhole and bring it back, you in principle create a tunnel to the past. But precisely at the moment that tunnel could first allow travel back in time, something extraordinary happens in the calculations. Quantum vacuum energy, normally a gentle background buzz, begins to surge without bound. What was once a calm conduit threatens to erupt with infinite energy, as if the wormhole mouth were trying to explode or collapse under the strain of defying time's order. It's as though nature booby-trapped the path to the past. Try to step through that doorway, and quantum fields themselves might bar the way, flaring up and destabilizing the portal. In technical terms, calculations using semi-classical gravity, a marriage of quantum field theory with general relativity's curved spacetime, revealed a pile-up of vacuum fluctuations. Particles and antiparticles, which usually flicker quietly in and out of existence, suddenly find a pathway to reinforce each other. Picture a photon, a particle of light, taking a trip through the wormhole, emerging in the past, then travelling back towards the wormhole and entering again and again and again. Each lap it makes, it arrives a little earlier and can chase its own tail indefinitely. The energy of that single photon can accumulate, like an echo growing to a cacophony in a circular hallway. The math suggests that this echo doesn't stay mild, it amplifies without limit. By the time the loop is fully available, the noise of these vacuum echoes might be so deafening that it shatters the wormhole itself. This dramatic feedback isn't limited to wormholes. Other proposed time machines face similar quantum rebellions. The Tipler cylinder, that endless spinning tube meant to curl time into a loop, runs into a different kind of roadblock. Hawking pointed out that constructing a finite, realistic version of such a cylinder would require exotic conditions, specifically some sort of negative energy or tension that normal matter can't provide. In essence, general relativity might allow a loophole in theory, with an infinitely long cylinder, but quantum reality refuses to supply the materials needed in practice. If you try to do it without exotic matter, calculations suggest it simply won't work. The universe seems to say, you can't get there from here. These observations coalesced into Hawking's chronology protection conjecture. He proposed that the fundamental laws of physics conspire to prevent closed time-like curves altogether. As he put it with tongue-in-cheek, it seems there is a chronology protection agency which prevents the appearance of closed time-like curves and so makes the universe safe for historians. That colourful metaphor conveyed the idea that physics itself steps in to enforce chronology. In more straightforward terms, any time you attempt to bend time into a loop, some instability or divergence will intervene, stopping you short of violating causality. The conjecture isn't a proven theorem, it's more of a guiding principle, born from examining one failed time machine proposal after another. But it carries a lot of weight in the physics community, because no one has yet found a convincing counterexample where a time loop could form without triggering some bizarre consequence. Quantum physics, often our friend in enabling new technologies, becomes a stern warden when it comes to time travel. Usually, we think of the quantum realm as strange and flexible. Particles can be waves, uncertainty abounds, impossible events happen with small probabilities. Yet here, quantum rules seem to flex their muscles to enforce something profoundly classical: the integrity of cause and effect. It's as if the fuzziness of the quantum world sharpens to a fine point, pricking any would-be time traveler the moment they push against the temporal boundary. Virtual particles that normally flit about harmlessly turn into a torrent of real energy to flood the breach. Space-time itself, so pliable in theory, stiffens in practice when twisted into paradoxical shapes. To be sure, this is all happening at the edge of our understanding. The calculations that predict infinite energy at a wormhole's mouth rely on our best approximations, melding quantum theory with gravity in a regime where neither is fully at home. Some physicists caution that a true theory of quantum gravity, something deeper than what we have now, might change the story. Perhaps the energy doesn't really become infinite, but instead triggers a gentle quantum correction that gracefully averts the time loop without a violent rupture. Or maybe there are delicate quantum states, undiscovered, that could hold a time tunnel open without instability. At present, however, every road we've charted to yesterday runs into a quantum roadblock or a need for physics be damned exotic matter. In a way, it's comforting. The universe protecting causality means we're not in danger of someone from the future popping into the present and rewriting history willy-nilly. There seems to be a built-in safety net, ensuring that the timeline we experience can't be easily tampered with by advanced technology. It keeps the what-ifs of paradox largely in the realm of fiction, at least for now. And from a practical standpoint, it means if we do pursue warp drives or wormholes, we might find their designs naturally limit us to causal travel only, no matter how much we tinker. Maybe the drive will simply refuse to go into a configuration that would create a loop, or its energy requirements will skyrocket beyond any achievable level if we try. Hawking's conjecture remains unproven, but it stands as a gentle warning sign at the edge of the known physical laws. Go no further, it whispers, lest logic and physics break down. Perhaps one day, a brilliant insight or experiment will show a viable path past that sign. But if the Chronology Protection Agency is real, it will be watching, ready to douse any nascent time machine with a bucket of cold quantum reality. For now, every hint we have suggests that attempts to violate causality will be thwarted by nature's own mechanisms. Time, it appears, has guardians at the gate. Still, scientists continue to poke and prod at these questions, because understanding exactly how the protection works could teach us new physics. It's like testing the locks on a forbidden door. Even if we never intend to break in, we learn how the lock is built. Some research even suggests small loopholes, special cases where quantum effects are tamer, or where exotic matter might be arranged just so. But no scheme has passed the gauntlet of peer scrutiny unscathed. Each potential model of a time machine finds its downfall, reinforcing the sense that chronology really is safeguarded. If chronology protection holds true, any warp drive or wormhole we ever build would likely come with built-in insurance against paradox. Instead of requiring human-imposed rules to avoid time travel, the very fabric of space-time might do it for us, cutting off paths that lead backward in time like a wise gardener pruning dangerous buds. In other words, nature would ensure our cosmic transports could never be misused to rewrite history. Such an outcome would be ideal. No need for time police if physics has already locked the door. But physics rarely gives a complete no without opening a window elsewhere. If direct time travel is out, we might wonder, are there other, more subtle cracks in causality's armor? Before exploring that, however, another layer of cosmic prudence beckons. Even apart from time loops, space-time can misbehave in other ways, exposing singularities or unpredictability. Just as we consider how quantum laws protect chronology, we should also ask how cosmic laws might keep space-time itself well behaved as we venture to bend it. Our journey continues gently onward. If the idea of time travel rattles the foundations of cause and effect, then the spectre of singularities haunts the predictability of physics itself. A singularity is a point where our equations blow up, where gravity becomes infinite, and the known laws cease to make sense. In a black hole's heart lurks such a singularity, but nature, in its wisdom, hides it behind an event horizon, a one-way veil that ensures no information from that abyss can influence the outside world. This hiding act is what physicist Roger Penrose conjectured as the cosmic censorship hypothesis. In essence, Penrose posited that the universe won't allow a naked singularity, one exposed for all to see, because that would be a breakdown of the orderly rule of cause and effect. Every singularity, he argued, comes draped in a cloak, like a horizon, preserving cosmic decorum. Why such fuss over a bare singularity? Imagine a region of space where unpredictability reigns, where physics can spit out any outcome without warning. That's the nightmare a naked singularity presents. Without a horizon to contain it, a singularity could, in principle, broadcast chaos into the universe. Determinism, the ability to predict effects from causes, would fail around it. For scientists and engineers, that's a horror story. It means a realm where calculations and expectations crumble. The cosmic censorship hypothesis, then, is a comfort. It's a promise, so far upheld in all observed phenomena, that however extreme things get, nature keeps the truly dangerous stuff under wraps. No peeking at the singularity allowed, no letting its wild influence leak out. When we dream of warp drives and wormholes, we inadvertently flirt with the edges of physics where singularities might arise. A traversable wormhole, if improperly made, or if it collapses, could spawn a singularity where the tunnel pinches off, a catastrophic failure of our shortcut through space. A warp drive, manipulating space-time on intense levels, might accidentally create horizons or regions of infinite stress if pushed beyond safe limits. In designing these technologies, we must heed the lessons of cosmic censorship. Avoid creating conditions that would lay bare a singularity, or better yet, avoid the singularities altogether. One practical approach is to insist on exotic physics that averts singularities from the start. For instance, traversable wormhole solutions generally require a form of matter with negative energy to hold them open. This exotic matter prevents the wormhole throat from collapsing into a singularity, essentially propping the tunnel walls against the immense strain of gravity. It's like reinforcing a mine shaft to stop it from caving in. If the supports hold, no collapse, no singularity. In warp drive concepts, careful field configurations, and again, likely some negative energy or other new physics, are theorized to stave off the formation of horizons or singular regions around the ship. By fine-tuning the shape and intensity of the warp bubble, engineers of the future would aim to keep space-time gently curved, never steep enough to tear or pinch off. Cosmic censorship also offers a guideline for what not to attempt. There have been thought experiments suggesting one might trick a black hole into revealing its singularity. For example, by overfeeding its spin or charge so that the protective horizon dissipates. So far, every attempt in theory seems thwarted. Some unforeseen effect kicks in to preserve the horizon. Similarly, if one tried to create a super extreme warp bubble that pushed beyond the brink, chances are some instability or horizon formation would intervene to stop the emergence of a naked singularity. It's as if the universe has circuit breakers. Push too hard on space-time's fabric, and it trips a switch. A horizon falls into place, or the structure disintegrates before it ever exposes an infinite abyss. For the architects of cosmic highways, this principle translates into design philosophy. Stay within the safe operating envelope of space-time. Don't crank the warp field to 11 if it risks spawning anomalies that can't be controlled. Ensure that any artificial wormhole has built-in containment, perhaps automated collapse mechanisms that safely shut it down if stability falters, rather like a nuclear reactor's control rods. In spacecraft terms, one might include a kind of singularity fuse that blows before any dangerous divergence occurs, sacrificing the drive to save the crew and surroundings. Such speculative safety measures echo a simple mandate: no naked singularities on our watch. Keeping space-time well-behaved isn't just about avoiding cosmic accidents. It's also about maintaining trust in the journey. Travelers and mission planners will want assurance that opening a wormhole won't inadvertently swallow a city or unleash high-energy chaos, or that engaging a warp drive won't rip a hole in the universe. Part of that confidence will come from physics itself. If cosmic censorship truly holds, certain catastrophes simply cannot happen. But part will come from conservative engineering, adding wide margins of error, multiple containment systems, and constant monitoring of the stress on space-time. Early warp ships might come with stringent limitations on speed or mass energy usage to ensure they never stray near those theoretical boundaries where things go haywire. Wormhole gateways might be surrounded by stabilizing fields and emergency shutoffs that kick in at the first hint of trouble. We might even see vehicles designed with quantum sensors that constantly check for any anomalous signals that would imply a violation of these rules. A kind of alarm system that alerts if some physics-bending experiment inadvertently tried to send information in a forbidden way. This sort of quantum watchdog would act like a silent referee, ensuring no experiment inadvertently breaks the cosmic rules. Its presence would let explorers push boundaries, confident that alarms will sound if anything truly impossible is attempted. Such safeguards help guarantee we work with the grain of the universe, not against it. In the cosmic casino of extreme physics, it's wise to bet that the house, the universe, ultimately wins. We may borrow the house's tools, gravity, energy, space-time curvature, to build wondrous devices, but if we overreach, the house rules apply. Cosmic censorship, whether an absolute law or just a prevalent tendency, nudges us to colour within the lines. If we do so, our cosmic highways can be laid out in harmony with the universe's own safety codes. We become co-designers with nature, rather than reckless drivers skidding toward a break in reality's guardrails. In practice, that means mastering the art of restraint even amid bold innovation, pushing boundaries, but gently, exploring frontiers, but respectfully. Such unity in perspective is as reassuring as it is profound. As we refine these designs, our journey gains not just speed, but a measure of wisdom. The cosmos has given hints about which paths are forbidden or perilous. By heeding the cosmic censorship hypothesis, we align our ambitions with a kind of cosmic common sense. Don't expose what should stay hidden. Don't unleash what can't be controlled. Following such common sense makes it far more likely we can venture boldly without inviting calamity. In effect, entanglement's wormholes remain sealed, just as entanglement itself carries no open signal for us to exploit. It underscores that to render a wormhole useful for travel or communication, we would need the same kind of exotic interventions required by any other faster-than-light scheme. And so, our focus shifts to those silent guidelines of reality, the principles of information that quietly govern what is possible. Not all the universe's safeguards are loud or violent. Some are whisper quiet, woven into the fabric of quantum theory, gently steering what can and cannot be done. Among these subtle guardians are the rules governing information itself. They don't grab headlines like wormholes or warp bubbles, but they ultimately decide how messages and matter flow through space and time. If we're to build cosmic highways that respect causality, we must pay attention to these quiet laws of information, principles that have no patience for cheating, duplication, or superluminal gossip. Consider entanglement, that almost mystical quantum connection that once made Einstein uneasy enough to call it spooky action at a distance. Two particles, light years apart, can be entangled such that measuring one seems to instantaneously affect the state of the other. To a hopeful starfarer, this might sound like a setup for an answerable, a faster-than-light communicator straight out of science fiction. But here's where the universe winks and says, not so fast. Yes, entanglement correlates results at a distance, but it carries no usable signal on its own. You and a friend could share a pair of entangled particles. When you measure yours, you get random outcomes of, say, up or down. Your friend, measuring theirs, also gets random ups or downs. Only later, when you compare notes via a regular, light-speed limited channel, do you see the spooky correlation. Your results mysteriously match up or complement each other in a way predicted by quantum theory. But crucially, neither of you could send a message or choose the outcome in advance. Entanglement is like a shared trick coin toss. You both get correlated flips, but neither can force heads or tails to convey a yes or no message. Yes, entanglement correlates results at a distance, but it carries no usable signal on its own. This is one expression of the quantum no-signaling rule. Despite nature's deep interconnectedness at the quantum level, it refuses to let that translate into superluminal communication. It's as if the universe allows a kind of cosmic harmony between distant particles, but forbids turning that harmony into a telephone line. This quiet rule preserves causality without any dramatic explosions or collapses. It simply makes sure that, even with quantum magic, you can't talk to someone in the past or faster than light. Every entangled system is subtly constrained. You can share correlations, but information, in the sense of a deliberate message, remains bound by the light speed limit. Another gentle but firm rule is the quantum no-cloning theorem. It states that you cannot make an identical copy of an arbitrary, unknown quantum state. To put it in simpler terms, you can't hit Ctrl+C, Ctrl+V on a single atom's exact quantum configuration. Why does this matter for our cosmic journey? Imagine a futuristic transporter or teleporter, the kind that scans you and reconstructs you elsewhere, perhaps across a wormhole or light years away. In classical science fiction, one might try to copy the information that makes you you and beam it somewhere else. But quantum theory stands guard. Your exact quantum state cannot be cloned. If you tried to duplicate a person's quantum information, or even a single photon state, you'd inevitably disturb the original in the process. The universe, it seems, does not allow perfect backups of its fundamental information. Why does this matter for our cosmic journey? This has profound implications. It means there's no trivial way to circumvent constraints by making duplicates. You can't copy a signal's quantum details to send one copy on a slower boat and another instantaneously, hoping one gets there faster. You can't duplicate the state of a particle in one location and instantly compare it with its twin elsewhere without losing something vital in the process. In the context of wormholes or warp drives, it suggests that any scheme relying on just copy and paste to get around speed limits will hit a quantum roadblock. We may be able to transfer information. Indeed, quantum teleportation is a real protocol that can move a quantum state from one particle to another at a distance. But even quantum teleportation obeys the rules. It requires a classical message, traveling at or below light speed, and consumes the original state in the process. No cloning, no cheating. This constraint has real teeth. There are no easy shortcuts through duplication. Any future communication idea that brushes up against this limit must fall back to classical light speed signals or suffer the garbling of information, reaffirming that there's no free lunch in physics. The no cloning principle also ensures consistency if we entertain time travel scenarios. One classic time paradox involves duplicating information or objects, like sending yourself knowledge from the future that you never originally acquired, creating something from nothing. Quantum law quietly says no here as well. You can't copy an unknown quantum state. If a future you tried to send back a perfect quantum copy of yourself, or even a book of knowledge, the act of copying would betray itself by quantum disturbances, or the information would get garbled. Perhaps this is another layer of protection. Even if a time loop somehow formed, the fidelity of information couldn't exceed what was already present, avoiding some of the pernicious self-creation paradoxes. Then there's the intriguing notion that entanglement and space-time geometry might be two sides of the same coin. In a bold conjecture, abbreviated as ER equals EPR, physicists Juan Maldacena and Leonard Susskind proposed that every Einstein-Rosen bridge, a type of wormhole, might be linked to an Einstein-Podolsky-Rosen pair, an entangled particle pair. In other words, perhaps whenever two particles are entangled, there's a tiny thread of space-time connecting them, a wormhole so microscopic and fast-closing that it's effectively impossible to traverse or detect. If true, this poetic idea ties quantum physics to relativity in a profound way. Entanglement would be the threads of space-time itself. Crucially, though, those wormholes, like the entanglement they represent, would be non-traversable. You couldn't crawl through them any more than you can send a usable message via entanglement alone. What could that key be? Some researchers suggest that to send a message through an entangled wormhole, one would need to do something extraordinary, like introduce negative energy, or manipulate the quantum system in a coordinated way from both ends. Essentially, you'd have to turn a non-traversable wormhole into a traversable one by adding a bit of the exotic. And even then, it wouldn't be an independent FTL channel, but a carefully orchestrated dance using both quantum and classical signals. At present, this remains theoretical musing. Yet the ER equals EPR idea hints at a comforting consistency. The reason quantum entanglement doesn't violate causality might be because any link it represents in space-time is fundamentally not passable. To get through, you'd have to obey the same energy conditions and exotic requirements that any warp drive or wormhole would demand, which likely circles us back to the need for negative energy or other constraints we've already encountered. In effect, entanglement's wormholes remain sealed, just as entanglement itself carries no open signal for us to exploit. It underscores that to render a wormhole useful for travel or communication, we would need the same kind of exotic interventions required by any other faster-than-light scheme. In practical terms, these quiet quantum rules will weave themselves into the fabric of any advanced technology we develop for cosmic travel. Engineers and physicists can't ignore them. A warp navigation system might incorporate quantum encryption to verify signals and ensure nothing can be faked or copied mid-transit, relying on no cloning to guarantee security. Communication networks linking distant wormhole stations might use entanglement for synchronization, but always supplemented by light-speed transmissions for actual data, accepting the no signaling limit as a given. Early warp ships might come with stringent limitations on speed or mass energy expenditure to ensure they never approach scenarios that could trigger causality problems. These measures sound complex, but they amount to working with the grain of the universe rather than against it. The cosmos quietly enforces consistency through these principles, and wise travelers will take heed. We often talk about pushing technology to its limits, but here we find limits that push back. They simply make sure that if you try to shout across the cosmic void, only echoes bounded by light speed answer you. And if you scheme to duplicate the secrets of the stars, you'll find those secrets strangely self-protecting. It's a gentle policing. No time cops in gleaming uniforms, just the invisible hand of quantum law. As we grasp these information rules, we start to see a bigger picture. All our efforts to travel faster or fold space ultimately funnel through the sieve of consistency. Entanglement hints at unity between space, time, and information, yet holds the line on causality. The prohibition on cloning enforces that information has an almost sacred integrity across time. These concepts teach us humility. Even with godlike technologies, we operate within a grand design that values coherence over convenience. Recognizing this not only keeps us out of trouble, but might also inspire new breakthroughs. After all, understanding why we can't do something often points the way to what we might do instead. With our minds attuned to the silent dictates of quantum information, we are better prepared to craft starships and gateways that tread lightly on reality's fabric. We'll know the difference between a door and a mirage, between a bridge we can cross and one that's merely painted on the canvas of theory. Before we finalize our mission plans, we should explore one more frontier of caution: the thermal edges of spacetime, where horizons warm and entropy looms, counseling us on the direction of time and the cost of our bold endeavors. It is a final gentle lesson from the universe before our journey continues. Even in the vacuum of space, nature whispers reminders that every extreme has its price. Push hard enough against the limits of motion or gravity, and the emptiness itself begins to glow with a faint warmth. This is not fantasy, but physical fact. An accelerating astronaut will perceive what a stationary one does not: a soft bath of heat known as the Unruh effect. In essence, the very act of rapid motion conjures up particles from the void, a quantum haze that warms the speeding traveler. It's as if the universe says, move fast enough, or twist space-time sharply enough, and I'll light a little fire for you. Nowhere is this more dramatically illustrated than at the edge of a black hole. Stephen Hawking's great revelation was that black holes aren't perfectly black. They emit a subtle glow, Hawking radiation, as quantum effects near the event horizon create pairs of particles, one falling in, one escaping. To an outside observer, the once hidden singularity announces its presence with this faint thermal whisper. Black holes, in dying, speak in heat and light, obeying a deep dictum of physics. You can't hide information absolutely, Entropy, the measure of disorder or hidden information, will find a way to increase. Hawking's insight tied together gravity, quantum theory, and thermodynamics, revealing that even the most mysterious regions of space-time respect the second law of thermodynamics, the rule that entropy tends to rise and that there's no free lunch when it comes to energy and information. What does this mean for our cosmic shortcuts? For one, any warp bubble or wormhole we conjure might come with its own horizon-like regions, boundaries beyond which events can't easily reach an outside observer. Just like a black hole's event horizon, a warp drive at superluminal speeds generates horizons, one ahead of the ship, one behind, that separate regions of space-time. And as physicists have pointed out, those horizons could radiate. A crew racing on a warp-driven starship might find themselves wrapped in a warm veil of Hawking-like radiation emanating from the warp bubble's edges. The faster the journey, the more intense this quantum glow could become, potentially threatening the ship or its occupants with torrents of particles. Nature, it seems, ensures there's always an energy cost to breaking the usual rules. In this case, the cost is paid in heat. Even traversable wormholes, if ever realized, would likely be no exception to thermodynamic bookkeeping. Feed one end of a wormhole with too much negative energy to hold it open, and quantum fluctuations may surge, as if the wormhole throat itself resists being propped open without consequence. One can imagine explorers stepping through a cosmic doorway, only to find that the act of keeping it ajar creates a kind of Hawking heat at the threshold. The message in all these scenarios is consistent. Horizons, whether artificial or natural, come with entropy attached. If you try to cheat distance or time, be prepared to deal with the energy and entropy that pour forth. The second law of thermodynamics, this ever-watchful principle, provides a kind of gentle guidance for the intrepid. It tells us that any process which reorganizes space-time or information will have a price in energy dissipation. In practical terms, it counsels caution. A starship might need robust shielding and cooling systems to survive the thermal fallout of extreme propulsion. A wormhole station might have to manage and vent enormous heat to keep its gateway stable and comfortable for travelers. Designs for these devices would almost certainly include radiators, heat sinks, or even novel quantum cooling apparatus to handle the constant drizzle or torrent of particles that come hand in hand with bending space-time. Thermodynamics also guards the arrow of time, the one-way march from past to future that we perceive. Though warp drives and wormholes tempt us with shortcuts, the second law reminds us that some arrows cannot be easily bent back on themselves. Imagine a scenario in which an advanced civilization tries to build a time loop to get unlimited energy or reset mistakes. The second law would intervene. Any closed, time-like curve, a loop in time, would create oddities like repeated systems where entropy could decrease, a big no-no in physics. It's widely suspected that such loops, if even possible, would either self-destruct under a deluge of vacuum energy, as chronology protection foretells, or be limited in ways that preserve overall entropy. In simple terms, you can't go back in time to get a cooler, more ordered universe without the bill coming due. The universe will balance the books. Seen in this light, the subtle warmth that pervades extreme realms is not just a technical detail, but a profound hint. It suggests that our cosmic highways, if ever built, will not be frictionless superhighways. They will be more like roads through a wild landscape, where we must occasionally stop to pay tolls. In this case, tolls of energy and entropy. Yet, understanding these tolls equips us. Forewarned by Hawking's equations and Unruh's predictions, we can engineer accordingly, turning what could be lethal surprises into manageable features. Perhaps hulls will be lined with metamaterials to absorb and convert stray radiation into electricity, literally powering the ship with the very Hawking radiation it encounters. Maybe the act of opening a wormhole will always be accompanied by a burst of thermal photons, which our systems could capture or divert. Cautionary as all this sounds, there is a comforting consistency to it. The same rules that forbid paradox and protect causality also offer a kind of insurance that the universe won't let us do something truly disastrous without warning. When horizons warm and particles dance in the void, they are communicating something fundamental. Proceed, but prepare. It's a gentle nudge saying that even as we transcend normal limits, we remain part of the tapestry of physical law. The heat on a warp bubble's edge, the glow at a wormhole's mouth. These are like the fever that tells a physician where the ailment lies, enabling a cure. They point us to the stresses in our designs, giving us a chance to reinforce or rethink. As we stand ready to set foot, or ship, on these new paths, the second law's counsel resonates. Take care of waste heat, mind the entropy, and respect the arrows of time. In the grand adventure of discovery, every guide, even a stern law of physics, is a friend keeping us honest and safe. And so, armed with knowledge of causality, quantum rules, and thermodynamic caution, we can envision voyages that honor those constraints. Our mission profiles can incorporate fail-safes for energy build-up, timing protocols to avoid loops, and treaties about not dumping heat or entropy where it might harm others. In short, we adapt, as we always have, turning challenges into checklists for safety. With causality protected, information respected, and entropy managed, one might wonder how an actual journey through a wormhole or via warp drive would play out when all these rules are observed. The final pieces of our puzzle lie in plotting mission profiles that thread the needle, achieving rapid transit while remaining firmly within the bounds of nature's laws. Our next step is to sketch such a voyage, blending all we've learned about paradox avoidance, cosmic design, quantum limits, and thermodynamic precautions into a practical plan for exploration. Onward, then, to charting a course among the stars that even the universe itself would bless as consistent and sound. If starships are to sail the cosmic seas without wrecking the timeline, their voyages must be carefully choreographed. Mission planners in this future age will need to think not only about fuel and destinations, but about reference frames and causality, like navigators once worried about tides and storms. One likely solution is to establish a universal time code, a preferred cosmic reference frame, perhaps keyed to the cosmic microwave background, or some galactic standard clock that all FTL travel must respect. In effect, before a ship engages its warp drive or enters a wormhole, it would synchronize with this master timeline, ensuring that whatever its journey, it cannot emerge in a prior era according to that master clock. By giving up a bit of the flexibility of relativity, acknowledging a universal time standard for travel, explorers gain consistency. Every departure and arrival gets time-stamped in this master frame, and paradoxical overlaps are headed off at the pass. Beyond just clocks, future vessels might be equipped with causality gauges or paradox aversion software. Picture a warp ship's onboard AI running thousands of what-if simulations before each jump. If any simulation finds a scenario where the jump would enable a message or object to loop back and affect its own origin, the AI issues a no-go. Perhaps the drive simply will not engage until the departure chronology is safe. It could be a bit like a rocket that won't launch if conditions are outside safe parameters. Except here the condition is temporal alignment. This sort of failsafe might be built into the very permits and hardware for FTL travel, the universe's equivalent of a circuit breaker that trips at the threat of a time paradox. Routes, too, would be planned with causality in mind. Just as ancient mariners followed trade winds, starfarers might follow causality winds, paths through space-time that minimize time bending. For instance, a ship might be required to take a longer route or wait at an intermediate port, say, a distant starbase, until a certain alignment is achieved that guarantees an unambiguous time order for all events. Such protocols could be enforced by a network of traffic control beacons. These beacons, scattered across systems, broadcast the universal time code and slot vehicles into FTL windows, approved intervals during which a jump won't upset cause and effect. Ships then travel in convoys or time-separated launches, much as airplanes follow scheduled flight corridors, but here the schedule is four-dimensional. Communication, often an overlooked aspect of missions, would also adhere to these rules. If a ship somehow circumvented the timeline with a message, it could inadvertently send information to the past. To prevent this, communication relays might deliberately introduce just enough delay or use specific routings so that even a laser or quantum signal never arrives before it was sent. One can imagine mission protocols where after every FTL hop, a ship must check in with the network and perhaps even wait for light speed confirmations from key waypoints, just to ensure nothing contradictory has occurred. It's a bit like calling home after a long flight to confirm you arrived, only here, home is confirming that causality is still intact. For added insurance, missions could incorporate the wisdom of the Novikov self-consistency principle into their planning. That principle suggests that if an event would lead to a paradox, the probability of that event drops to zero. Only self-consistent outcomes occur. While this is more philosophical, or perhaps a law of physics, than a tool, mission designers might simulate scenarios with that principle in mind. They could analyze a planned trajectory for any potential closed loops and ask, if we do this, could any sequence of events create a contradiction? If the answer is yes, then either the mission profile is altered or one trusts that nature itself will intervene to make it impossible. Either way, one avoids betting against the universe's logic. All these precautions might sound onerous, but to future explorers, they could become second nature. Just another set of flight rules. In the early days of aviation, pilots learned to navigate by radio beacons and adhere to new rules to avoid mid-air collisions. In much the same way, Starship crews will learn the rhythms of safe FTL travel. They'll file flight plans through time and space, get approval from a kind of temporal air traffic control, and carry on. Their navigation displays might highlight regions of space-time to avoid, perhaps zones where gravitational fields or prior jumps create higher risk of frame misalignment. Their ship's log might be automatically audited to ensure chronology was preserved, a post-mission causality report filed alongside the cargo manifest. The result of all this careful planning is that voyages remain adventures, not fiascos. A ship might jump from Earth to a distant colony in minutes, but due to cleverly imposed constraints, both ends agree on an order of events. The colonists see the ship arrive after it departed Earth, no matter how fast it travelled, because all the while it was riding within the bounds set by an agreed cosmic timetable. Should any incident occur, say a misjump or an equipment failure that raises even a whiff of paradox, the crew would follow strict protocols. Perhaps the ship and its passengers would be temporarily quarantined until timelines can be verified, or certain data, like observation logs, might be rolled back or sealed until consistency is confirmed. In extreme cases, one imagines a vessel might even be ordered to loiter in a remote region of space, isolated, until any causality confusion dissipates
an echo of how we quarantine travelers for health reasons, but here for timeline contamination.
Through these measures, interstellar society would gain confidence in FTL travel. What once seemed like an invitation to chaos becomes, by discipline and design, almost as orderly as catching a train. The universe's basic laws remain unbroken, even as we bend our paths through the stars. With reliable mission profiles that respect every causality constraint, we can truly open the highways between worlds. But establishing technical guidelines is only part of the story. There will also need to be agreements, laws, and cultural norms that transcend any one ship or crew, guiding everyone who steps onto these fast tracks. For that, humanity, and any other species we meet, will turn to governance, philosophy, and shared stories to navigate the ethical and societal implications of mastering the space-time continuum. The dawn of faster-than-light travel would not only spark engineering challenges, but also a need for new rules and understandings among societies, just as the advent of seafaring drove maritime laws. The advent of warp drives and wormholes would drive space-time laws. Nations and worlds might convene to sign agreements, perhaps a chronology convention, pledging that no one will intentionally tamper with history, nor use these technologies as weapons against causality. It could be akin to nuclear treaties of the 20th century, a recognition that certain powers, if misused, endanger all. An accord might declare that any attempt to create a destructive paradox, say, deliberately causing a timeline where an enemy's past is altered, is a crime against all sentient life. Such an understanding would be both practical and moral, establishing time tampering as taboo and subject to highest scrutiny. One concept likely to emerge is time sovereignty. This is the idea that each civilization or community has the right to its own timeline's integrity, free from outside interference. Violating a planet's time sovereignty, say, by sending agents to meddle in its past, or by dumping entropy into its region via careless experiments, would be seen as a grievous breach of galactic conduct. In a way, time sovereignty extends the idea of territorial sovereignty into the fourth dimension. Not only is a planet's space its own, but its history is too. Respecting that may become a point of pride and principle. We can imagine cultural norms developing, stories of heroes who protected their timeline from corruption, or cautionary tales of those who broke the rule and brought ruin. Liability and insurance would also take on mind-bending dimensions. If a warp jump gone awry could, in theory, ripple into different eras, who pays for damages? Lawyers and insurers might grapple with scenarios that once belonged only to fiction: chronal damages and temporal liability. Perhaps, to everyone's relief, physical law prevents most of those nightmares. But even so, more mundane issues remain. If a ship's warp field irradiates a nearby habitat with a burst of Hawking radiation, or a wormhole's exit causes a minor quake on the host planet, the responsible party would need to be held accountable. Regulations would likely mandate safety distances for endpoints, e.g., no opening wormholes too close to populated areas without permission, and safe throttling of warp fields within planetary systems. Just as today we have no-fly zones, tomorrow we might have no-jump zones around sensitive regions, say holy sites or protected natural wonders, to prevent unwanted temporal or gravitational side effects. Culturally, humanity, and any peers in the galaxy, will need time to adapt their worldviews. Our myths and science fiction have fortunately given us a head start. Generations have grown up on tales of time travel paradoxes and prime directives about not interfering with less advanced worlds. These narratives may well serve as informal guideposts as reality catches up. When the first explorers venture out, they'll carry not just instruments and supplies, but also the collective wisdom encoded in 1,000 cautionary tales. Society might celebrate the heroes of exploration, but equally venerate the guardians of time. Perhaps a new kind of professional whose job is to monitor and advise on temporal integrity. This wouldn't necessarily be a shadowy time police force. It could be as simple as a council of scientists and ethicists who review proposed high-risk experiments or missions for potential chronology issues. Education and public awareness will also be crucial, just as every child today learns that energy must be conserved or that pollution can harm our environment. Children of the warp age may be taught from early on about causality and entropy. They'd grow up knowing that certain things, like trying to send information to one's younger self, are not just bad form, but fundamentally unwise. Perhaps there will be thought experiments and classroom demonstrations with harmless simulations to show why we don't, say, schedule a message to arrive before it's sent. By instilling a respect for time's order early, society creates a culture of self-regulation where people intuitively avoid pushing boundaries that could unravel their reality. In governance, new agencies or departments might emerge. One could imagine a temporal affairs bureau as commonplace as today's environmental protection agencies. Its remit: to oversee use of time-bending technologies, investigate any anomalies, and maintain public trust that our timeline is secure. Such a bureau would work closely with space agencies and research institutions, ensuring that innovations stay within agreed safety parameters. They might license wormhole generators only to vetted parties, require warp drive vessels to carry black box recorders that log their temporal data, and enforce the sharing of that data for audit. Through all these structures, laws, treaties, cultural narratives, and institutions, we as a civilization create guardrails for ourselves. They don't exist to stifle progress, but to shepherd it, to make sure that when we run, we don't trip over our own shoelaces. Humans have a long history of doing this. We developed rules of the road when cars arrived, flight regulations when airplanes took off, and international agreements when the first satellites went up. Each time, we balanced excitement with responsibility. The cosmic highways of wormholes and warp drives will be no different. Yet, unlike cars or planes, these highways come with existential stakes. They touch the foundations of reality in a way earlier technologies did not. That's why the law we build around them will be so important. Already, even before the first warp test, we tell stories of time mishaps and miraculous saves. This shared law, from the ancient myth of Kronos to modern time travel epics, serves as a moral compass. It reminds us that great power over time and space demands great care. When the day comes that a captain plots a course to another star through a wormhole, she will do so within a framework of both regulations and wisdom traditions. In her hand might be a treaty document, but in her mind will be the echoes of all the cautionary tales that guided her society to this threshold. In the end, these measures ensure that as we break boundaries, we do not break ourselves. We will step onto the cosmic highways boldly, but also wisely, with one eye on the stars and one on the ticking clock that has always grounded us. Laws and law together will help us carry our humanity, our sense of right, responsibility, and wonder into the vast beyond intact. And with that, we can finally turn to the adventure itself. Voyages that take us across the gulf of space in a heartbeat, all while keeping the fabric of reality unscathed.